So we are waiting for Brijesh Bhai for live streaming. As soon as Brijesh Bhai will do live streaming, okay, now we can start.
Okay.
From Parul University extends a hearty welcome to all the dignitaries, Dr. Amin Patel Sir, Provost Parul University, Dr. H.S. Vijaya Kumar Sir, Registrar Parul University, and all the participants to this two-day International Digital Conference on Applied Mathematical Sciences organized by Parul University and Gujarat University mutually. From Gujarat State, India. This symbiosis of series of successful events between Parul University and the Gujarat University since 5 long years has been so productive that this year we have planned this international conference with an overwhelming response of 650 participants globally. We welcome you all on this.
Internet is a big problem. So voice is not coming.
Kanan, unmute yourself. Kanan, unmute yourself.
So, while studying mathematics, a question often arises in one's mind. If mathematics is everywhere, how can one exactly implement it to make this modern world and life easier and high-tech? What do you say, Puri ma'am?
True, ma'am, I agree. I am Puri Pandya from Gujarat University, and I welcome you all to this two-day international conference on applied mathematical sciences. Well, such conferences where assorted stalwarts come together to shower the cognitive knowledge and techniques is an answer to such ambiguities on advanced application of mathematics. However, applied mathematics has not left any field untouched, be it engineering, medicine, or biology. It has unveiled enormous secrets of the how and why and beneath the practical, logical, and technical aspects sustaining the world.
Today, we have experts from assorted disciplines of the said subject on single platform, extending the opportunity to engrain the best they have. With immense exaltation, I welcome all the dignitaries on behalf of the Gujarat University and the Parul University. Firstly, we have Professor M.D. Haider Ali Biswas from Khulna University, Bangladesh. We welcome you, sir. Professor C.S. Lalita ma'am from University of Delhi, India. Thank you for being with us, ma'am. Professor Neeta Ed Shah ma'am from Gujarat University, India. We are extending a warm welcome to you, ma'am. Colonel Dimple Kumar Chali Sajar from Virginia Military Institute, VMI, Lexington, USA. We welcome you, sir, for your immense presence. We also welcome Professor Christ University, Bengaluru. We also have with us today Dr. Alberto Shikongo, University of Namibia, South Africa. Both of you are welcome for your immense presence today, sir. Thank you so much for joining us. Professor Rajrani Bhargava ma'am from Indian Institute of Technology, Roorkee, India. Welcome, ma'am. Dr. Jitendra Kumar Singh from Hanyang University, South Korea. Thank you for being with us, sir. I welcome all the dignitaries on behalf of the family of Gujarat University and the Parul University. I also welcome Dr. Amin Patel, sir, and Dr. Vijaya Kumar, sir. Dr. Amin Patel, sir, is a provost of Parul University, and he is a visionary man. He has a huge experience in the academic field as well as in the leadership field. He has a master's as well as PhD in civil engineering, and he is with us today, gracing this beautiful occasion of international conference together. We also have Dr. H.S. Vijaya Kumar, who is Registrar of Parul University with over 37 years of professional experience during which he has held positions in teaching as well as in administration. He has a PhD in agricultural economics from Indian Agriculture Research Institute, New Delhi. We welcome you, sir, for sparing your valuable time and blessing this conference with your presence. I once again welcome Dr. Emin Patel, sir, and I request him to say a few words. Please, sir. Emin Patel, sir.
And all. Hello.
Yes, sir.
I am audible to all.
Yes,
Hello.
sir. We can hear you. Yes, sir.
Ji,
We can
namaskar
hear
to one and all. No doubt, it's indeed a pleasure for me to be a part of this today's program. No doubt, it is of Applied Mechanics Department, and it is an international conference. I can say that, where we have seen that the resource persons are from abroad too, Bangladesh, USA, and so on. Obviously, this is said to be in the international conference when there is a contribution or resource person are from various parts of the globe. Now the globe became just like a village, so everything we can connect, sitting either India with Europe or USA, everything is visible. And today we are realizing, no doubt Corona has compelled us to do that faster, but it is a good sign that we can connect anyone across the globe. Only limitation is that our connectivity, or rather sometimes that poor bandwidth, so we cannot hear each one properly. But hope so that this effort which we are making, and coming day we are going to be more and more improved in that. And with that connectivity and with bandwidth, obviously this type of learning will consider to be one of the best, or rather the only solution of all problems. So by this, no doubt it belongs to applied mathematics. Obviously several issues or cases are to be discussed, and as I have told to not to speak more than 2 minutes, so my best wishes to all of you, and hope so that the success of this for coming 2 days. Thank you very much. Over to you, Kanan.
Thank you so much, sir, for your valuable words. We really appreciate your presence here. Thank you, sir. So not wasting much of our time, as we all know that we are keen to take a studious flight for the conference, let us kickstart the conference. Over to you, Puvi ma'am.
Yes, ma'am. Thank you, ma'am. Our first session for day one will be put through by Professor Mohammad Haider Ali Bishwas, Professor of Mathematics from Khulna University, Bangladesh. Bestowed with PhD in Electrical and Computer Engineering from the University of Porto, Portugal in 2013. Professor Haider has more than 20 years of teaching and research experience at different public universities in Bangladesh. He published 3 books, 5 book chapters, and more than 150 research papers in the peer-reviewed journals and international conferences. Professor Bishwas has worked at several R&D projects in home and abroad, particularly different research projects funded by the Ministry of Science and Technology, Bangladesh University Grant Commission of Bangladesh, and the World Academy of Sciences. Recently, Professor Bishwas has been elected as a member of Executive Committee of Bangladesh Mathematical Society for the year 2020-21, and also nominated as the Associate Editor of the International Journal, Ganit, Journal of Bangladesh Mathematical Society for the year 2020-21. There are other numerous memberships and project works in the basket of Professor Bishwas. Today's topic is optimal control applied to epidemic models of emerging diseases. Welcome you, sir. I now request him to begin with his presentation.
Thank you so much, Probi. Am I audible?
Yes, sir. Yes, sir.
Okay, thank you, everybody. And my slide is okay? Everybody visible too?
Yes, sir. Yes, sir.
Okay. So first of all, I would like to thank to Parul University and Gujarat University, who are jointly organizing this international prestigious conference during this pandemic situation. And I am deeply acknowledged to the organizer for giving me an opportunity to share my research with the global experts, audience, and some researchers working in this biological application of mathematics in biological area. So The title of my topic is actually Optimal Control Applied to Epidemic Models of Emerging Disease. So from beginning, I would like to split my talks about some theoretical aspects and then some applications of optimal control in biological, especially in epidemic model and especially emerging disease. And I will show two applications. Okay, so this is actually the outlines of my talks. Here you can see I will discuss first the very theoretical backgrounds of optimal control, because actually most of the researchers here are, I believe that some of researchers are very young and students, colleagues, so they need to know actually the basic background, basic difference between optimization problem and optimal control problem, and then some theoretical aspects for the solution of optimal control problem for the existence and uniqueness verification. And then I will show two examples, especially in communicable disease. One is for the emerging disease is chronic HIV immunological model, and then another is the recent pandemic disease like COVID, but I will show a general SAR type model with vaccination strategy, how control theory can be applied and give a better strategy for this treatment or prevention control strategy. So very beginning, actually, I would like to mention the optimization problem, because optimization is a vast area in dynamic, especially in mathematical optimization. So optimization, what we do, it is an act or it is a method or achieving the best possible results under some given circumstances. Actually, these circumstances means some special conditions, or we call constraint. More precisely, we can define it optimization actually the process of finding the condition that give the maximum or minimum value of a function. So this is a very basic foundation optimization, and here you can see the general optimization problem in mathematical form. This is the very general form. Actually, we would like to maximize or minimize a function subject to some constraint. This constraint may be inequality or equality. All these function here, actually the function f, this is called actually the objective function, and each other g and h both are the constraints. Z is the inequality constraints and h is the equality constraints, and x also it is the set, it should be closed and bounded. So this is the very general form of optimization problem. So we can have a solution technique, because it is very familiar within a vast area of optimization in mathematical application. So the optimization, the solution actually X, which satisfies all the constraints, we call this type of solution is a feasible solution. So there is a lot of feasible solution. It may happen for the solution, the existence of the solution of this optimization problem, and all the solution sets is called the feasible region. I will discuss, I will show a very motivational example here. And all these feasible solutions which satisfies our objective functional, either maximization or minimization, we call the solution is optimal. So in that case, this X is denoted by X star. So this is the optimal solution. There is a lot of theorem, which grant is the solution of this type of optimization problem. One important theorem is the bias theorem. Actually, who the colleagues who are working in this area, we know this. We know all this type of theorem. So this, if X is non-empty and compact, that is closed and bounded must be, and f is a continuous function, then this minimization problem must have a minimum solution. And when the solution will be global, actually the solution should be global if this function is a convex optimization problem. So this is a very important and a powerful theory for the optimization problem in general, mathematical optimization. And this is the very common and very motivational example. You can see here, we should minimize a function f subject to some constant g1, g2, and g3. And if we see that f is actually a contour, that is a circle, so we should minimize the area of the circle and satisfying the constant g1. So g1 is actually this, you can see, is a parabola, g2 is a straight line, and g3 is a straight line also. If we satisfy these three constants at a time, these are shaded area is the feasible region. So we have a lot of solution in this feasible solution area, this shaded area, but all the solutions only except the optimal solution occurs at 2 and 1, because if we would like to satisfy the constant, we should minimize our contour set at the point 2, 1. So this is very important and fundamental optimization problem. What is noted here, actually, all this type of problem is looks like algebraic problem. So algebraic problem actually the baseline of the optimization problem. So now I would like to discuss about the dynamic optimization problem, because a class of problems where in the global optimization where dynamic variable is involved. So this is the most important thing for the dynamic optimization problem. And these dynamic variables changes over the time. And actually this type of problem appears and exists in our optimal control application. So I will discuss in the next application in this area. So the dynamic optimization is very fundamental, because this dynamic optimization have a close connection with optimal control. And you can see here that's very general form of this type of dynamic optimization problem. So dynamic optimization, it looks like the similar way. We should minimize a function j, and you can see here j is a function with two variable, a state variable, you can see x and y, and also another variable is input variable u, we call it control, subject to some constant as well. And this constant, actually you can see here, the constant f is the dynamic state equation. So this is very important and fundamental for distinguishing optimization problem and dynamic optimization problem. So f is the dynamic equation, so that is the differential equation. C is the initial conditions, and h and g both are the point constants, and this constant should be also have the dynamic or algebraic. And also the other constant is the general algebraic constant. So variable x and y, but y is the time invariant continuous variables and x is the dynamic state variables, and u the control variables. So it is important here, if u is not appearing here, that is u is absent here, this problem should be dynamic optimization. But when u is present, this type of dynamic optimization, this problem would be a optimal control problem, because control variable u is existing here. So this is actually the fundamental difference. Here you can see the optimal control theory. Actually, this is also a very important branch of optimization, where we mainly aims to find a control strategy u for the dynamical system over a period of time, such that the objective function is maximized or minimized under some constant, under some specific constant. So the objective function and the dynamic system, it is important here. The dynamical system you can consider in different states, because we can, if you see a spacecraft is one kind of dynamical system where rocket thrust may be the control, and our objective may be to reach the moon with minimum fuel expenditure. So this is one kind of dynamical system. Another dynamical system may be our national economy, where objective is to minimize our unemployment problem, and in that case the control should be our fiscal or monetary policy. So there are different ways we can define the dynamical system. Even a human system also we can consider a dynamical system, because in suppose for the infectious disease, we want to minimize, we want to reduce our infected population. So this is one kind of dynamical system, and here control should be our the basic strategy how we can follow, that is for the social distancing like this, and mask wearing mask. This is maybe the control strategy. And so objective is to minimize the reduce infection or to eradicate the disease. So dynamic optimization actually coincides with optimal control when the control variable is associated with the objective functional. So this is the very most fundamental distinction between dynamic optimization and optimal control problem. So now I will go to basic foundation of optimal control problem and its existence for the solution of the theory. So there is a lot of history about more than 350 years ago. Actually, this type of problem was appeared, but still this is a very influential area of application of area of topics of research in the in our real life situation. But this problem, optimal control problem, it comes actually as a generalization of calculus of variation. So calculus of variation is a very fundamental and one of the most least time of control problem in the Brachistochrone problem we actually know in our analytical topics in classical mechanics. And Leibniz, Bernoulli, Jacob, Bolsa, all scientists, the contemporary scientists, opened this type of problem, and we know the history of this type of calculus of variation. But at that time, there was not a general solution for solving this type of optimal control problem. So the milestone or tremendous achievement were achieved in the 1958 during the Pontryagin and his researchers for discovering the solution set, that is we call the set of necessary conditions for optimal control problem for the solving for a solution of existence. And this type Pontryagin maximum, we call it Pontryagin maximum principle, or it should be minimum principle depending on our problem. And afterwards, in 1973, Francis Clark, he was another founder of this optimal control for distinct a discovery of non-smooth optimal control technique. So this is the set of necessary condition for the non-smooth case. So this is a very milestone in solving optimal control problem in the area. And calculus of variation, actually we are very familiar with this type of problem. This is the problem of integral type functional. We would like to minimize this functional, that is we would like to find an arc x star which minimizes this type of integral. This is the fundamental problem of calculus of variation, and here all the boundary condition as well, and L actually the function of the of this integral function to be maximized or minimized. So depending on this calculus of variation, actually this problem has a connection with our optimal control and the dynamical system. You can see the problem we define in the dynamical system is looks like this one. X dot is a function of t and x. So the x is a state variable here, and t is the independent variable, that is time. So this x depends on the time, and when this type of dynamical system we have an external force to control or to minimize or maximize, have a mechanism, we put this control variable, that is u. So this u is the control variable, and this system is actually then we call it controlled dynamical system. So this control dynamical system is actually involved in optimal control problem. That is, all these systems are differential equation, whether it is linear or non-linear, but most of the cases the differential equation are non-linear, and it is ODE, but there is also different application in PDE. So this type of problem usually we will discuss here, the application of non-linear ODE and the optimal control problem. And as usual, as you can see, our aim is to find such and control who is maximize or minimize our objective function. And this objective function looks like this objective function, actually the Bolsa type and standard Bolsa type objective function. I will discuss in the next slide. And U is also have a control between in a set of the measurable function. So this U, capital U, is the measurable set taking the values of U. So this is the very general form, Bolsa type optimal control problem. So now we can see here, you can see the minimize, you can have the minimization function, and subject to some constraint. This constraint, first constraint, is a dynamic constraint, you can see here. So this is the very main distinction between optimization and this dynamic optimization. And the second condition, that is the constraint, is actually, this is the state constraint. This constraint in this case is a mixed constraint, because here both u and x are presenting here, and u is constant in the measurable set u, and all the our boundary. This is actually the initial condition, because our in the terminal time is free. So this is a free time, and this is a fixed time of optimal control problem and initial value problem. So all these functions actually are defined here. So this is the very general form of optimal control problem. But this problem, our objective function has two parts, you can see. So objective function, first part is the terminal cost. This in the economical model we call the salvage cost, and the second part actually the integral cost, and this cost is actually running cost. These two types. If one cost is absent, then we call in different way. We can define 3 optimal control problem depending on the cost functional. So you can see when our objective function contains two cost, both it is called the general type, standard, or Bolsa type optimal control. But when the objective function, the integral term, that is the L, is absent, this L is absent, we have only the Mayor type optimal control problem, that is the initial condition, that is the salvage cost. And when the Lagrange type only appeared in the problem and the salvage cost is absent, this is the Lagrange type. So this is very 3 unique optimal control problem. But the very good understanding is that there is a good connection between 3 types of problem, and we can easily convert one type of problem to another by applying a penalty function or a state augmentation technique. But it depends actually the solution technique, which is better for our solution strategy. So this is actually very easy type for converting any type of optimal control problem to other type. I will discuss here a very important, another important thing is physical constraint, because the problem I will discuss here and the application I will show in two epidemic model. Actually, I will have used here two state constraint and also mixed constraint to have a very better strategy and very good results using ordinary optimal control problem. So constraint, actually I already discussed, both type of constraint is very important in optimization problem, and sometimes many problem have solution, better solution using the constraint. So this constraint have equality and inequality, I already discussed, and these you can see the first constraint is the mixed constraint, because state variable and control variable both appearing here, and the second condition is the only state constant, because state constant only have a state variable, though only state variable is appearing, but this type of constant is actually very complicated for the analytical solution. But actually we don't be worried, because there is a lot of theorem already we developed, and also there are a lot of theories in the literature for solving this state constant problem. So this is very fundamental physical constant. But there is another control constraint is isoperimetric constraint. This constant have some limitation, I will discuss in our example there. So the the fundamental idea for solution technique of this type of optimal control problem is like this in the figure in the right side. You can see our target solution. We would like to find U star in such a way that our objective function is minimized or maximized. In that case, our state variable also in that case, the state variable we obtain is x star. So all the x star and u star, this pair of solution is called the optimal over all feasible solution. So in the right side in figure you can see the red one is our optimal solution, but the maroon color is it actually we have the all feasible solution I already discussed in previous optimization problem. So it is the very fundamental set of necessary condition, because this is important after Pontry again and his collaborators. because optimal control has a set of necessary conditions, and this condition also in some case sufficient also. But here I will discuss the set of necessary condition depending under the Hamiltonian function. So this Hamiltonian function actually is defined with our objective function and also our dynamic constant that is subject to the dynamic constant. And here you can see the P. Here P is actually the so here P, you can see the P is the co-state variable. So all state variable have a shadow variable, co-state variable, and alpha actually for the normal case. We consider usually normal case because otherwise abnormality appears and the solution may be degenerate solve. So we consider alpha equal to 1. So this is the set of necessary condition. First condition actually the optimality condition, because when we partially differentiate H Hamiltonian with respect to U, so this U should be 0. This the derivatives, first derivative should be 0 at the point U star, that is optimal solution. And the other condition actually the adjoint equation. This adjoint equation have two kinds, is the state equation and the co-state equation. And the last condition is actually the transferability condition. So this is the very general formation without a state constant. So when the state constant appears, the solution will be a little bit different. I will discuss in an example. So next, the important thing is when Pontryagin maximize principle, how we can define and how we can explain. The Pontryagin actually discovered this type of condition. When optimality condition in the previous slide, we can see if we differentiate H with respect to U, in that case, we don't put any constraint on the control. But when our U, we cannot have sometimes unrealistic solution, or if we don't put any control, any bounds on the control variable. So control should be bounded also. And in that case, this bounded control, applying this bounded control, Pontryagin called this type of condition is the Pontryagin minimum principle or maximum principle, and the condition looks like in this one, in the last one, the is Hamiltonian, and it should be at the optimal solution. This should be minimized. And important and very fundamental achievement of this Pontryagin maximum principle is that Pontryagin maximum principle are actually both necessary and sufficient for, but optimality condition is only necessary. So this is actually very strong condition for solving optimal control problem in our present realistic situation. So now I will discuss here just theorem under which all the solution exist and the solution should be unique. So this is called the existence of the optimal solution. In that case, we should prove this theorem, but this theorem already proved in our research in the previous, in our PhD or some in other application in our different papers, in the scientific papers. And this is the very fundamental theorem we have already proved. If we consider all these functions, and if we prove that L, small l, capital L, F, G, and H, all these functions are continuous in X, and our Z is the bounded function, and U is compact. Also, the control set U is compact, and our objective function, that is U, L, is convex. In that case, at least our objective should have a finite value, and this problem has a unique solution in that case. So this is the very important theorem for the existence of the solution. I will discuss in our application. So now I will go for application in our real life, especially in the emerging epidemic disease. So optimal control actually have a very long history in modeling this nonlinear behavior of human physiological system inside the human body, because the mysterious mechanism of host-pathogen interaction in the body is very challenging to find out a very good prevention or control strategy. But our modeling, especially application of mathematical modeling with the help of optimal control technique, have successfully modeled this type of phenomena of inside the body and then we can design to understand the evolution of the disease dynamics. So this is actually important in the application of controlling this type of disease in our everyday life or in our human physiological system. So there are two types of actually emerging, very recently emerging and re-emerging disease have a panic, have a threaten globally, and all this type of emerging disease we will consider here two application of this emerging type disease. But I just mentioned some emerging disease. You can see the emerging disease actually those type of disease which are previously unknown disease. Sometimes it is known and rapidly increasing incident in geographic range at least 2 decades. So persistence of these infectious disease that cannot be controlled. All this type of emerging disease. Sometimes re-emerging disease also appeared, and re-emerging means the reappear of the disease after they have been on a significant decline. All these re-emerging disease have emerging and re-emerging disease, Ebola, HIV, and our present pandemic, MERS and SARS coronavirus. So Hanta virus, that is Nipah virus, dengue, West Nile virus, Zika virus, chikungunya. So a lot of infectious emerging disease are existing in the society now presently. So we are facing a very health hazard globally, and we are very much worried about all this type of disease. So I will discuss only two applications. One is HIV, that is the very pandemic, global pandemic disease, and is also the chronic disease, you can say, using heart treatment. And another application I will discuss here, the very basic general share type model with vaccination as the control strategy. So first, I will discuss the immunotherapeutic treatment of our HIV positive patient using heart treatment. So actually, what is heart treatment? We should know heart. Heart means highly active antiretroviral therapy. So this is in the present situation only the effective treatment strategy for the HIV patient, because until we don't have a vaccine for the fully cured HIV-free world, we should have the treatment for this type of HIV patient, and this treatment depending on the depending on the nature of the disease, that is the existence of the disease, and usually doctors use this disease as a multiple combination of the drugs. When the drug is multiple combination, at least 3 drugs, we call this type of disease combination is heart. So heart is actually very effective way, and at least we have a very evidence that 2 cases at least in the globally, one is in USA, another is in Europe, that is in Germany. The 2 patients have been cured fully functionally using the heart treatment. So this heart treatment, if we detect the disease, if it is possible to detect the disease in the earliest stage, and in that case, the HIV virus is possible to using heart treatment. So this is very fundamental. But all this treatment actually is our immunoboosting development, because immunotherapy is the mostly variety of the chemotherapy. So one kind of immunotherapy, it depends on some drugs which not only kill our pathogen in the body but also help increasing the long-term internal resistance of our immune system, so that the body itself can fight against the virus. So this is actually most important treatment strategy nowadays until we don't have vaccine. So milestone also have, I already discussed that remarkable milestones toward the antiretroviral therapy have been achieved in the last 10 years, and functional cure also have been achieved using the heart treatment. And also we have some development for discovery the vaccine of the HIV anti-HIV vaccine, but still we have to wait for a HIV-free world for a fully cured vaccine. But until that, we need to treat our patient using antiretroviral therapy, and this is actually the treatment strategy for the we can apply for the control in application. So now you can see here, I will consider a model, and the model actually was developed first, DICAMS and Webb. I will discuss in the next slide. But here only the very simple deterministic model. If we consider our immunosystem, that is our white blood cell, we call it CD cell 4, and another for the virus cell. So only two state variables are representing the whole system, the CD cell and the virus cell. And all the other cell, this is the actually the natural death rate of the CD cell, and lambda is the infection rate, also gamma the input rate of the external virus source, alpha the loss of rate of the virus. All this is the source term for the uninfected cell, CD cell, that is uninfected cell, we have the source term, and natural loss of the uninfected cell using the virus concentration. So using all these parameters, we can develop the model of the Hiv immunology. It was first proposed in 1998 by Krishna and Webb. You can see we don't use, Krishna and Webb did not use any control strategy in that case. They only studied a mathematical model to propose a treatment strategy using the immunoboosting of our immune system. But in 2002, Hemraj Joshi extended this model using optimal control. So this is the application of optimal control on the Hemraj Joshi applied in his model. You can see here two control, one is U1 and another is U2. These two control was applied to modify this optimal control problem. And U1 is actually immunoboosting drugs, and also U2 is our virus suppressing drugs. So the two types of drugs usually we use here to boosting our immune system or to develop our immune system as a control variable. So this control variable using this on our objective function is to minimize the objective function here. You can see we can minimize this objective function, but usually we use minus t, that is the CD cell should be maximized. In our case, we would like to maximize our CD cell, and at the same time we would like to minimize the systematic cost of the immunoboosting drugs and the viral suppressing drugs. That is, the systematic cost should be minimized because there is a lot of hazardous side effects for using this anti-retroviral therapy or highly active anti-retroviral therapy. But here our control set should be Lie-based measurable set I already discussed, and you should take the values from 0 to 1. This is actually some a probabilistic sense, because when the control is fully effective, we call the value of U is 1, that is the maximum dosage we can use over the time, and when U is 0, that is no dosage is applied for the treatment strategy. So this is the very logical way to take the values of U as 0 and 1.
Excuse
So
me, sir.
Yeah.
It is the last 5 minutes.
Okay, so the optimal control, actually the problem we can define here. This is the main problem, and all the variables here is discussed and in our previous in the theoretical stage, and here we just define this optimal control problem in our optimal formulation technique. But the one is the remarkable extension of this type of work is we did it in the 2019, and it already have a good published in a very good journal that we would like to use the state constant, because state constant keep our virus cell at a minimum level, and the state constant actually represents our highly active antiretroviral therapy. So highly active antiretroviral therapy can reduce the virus cell at a minimum level, and I will show in our discussion. And in this extended model, in the state constant model is like this, and all the maximum principle I already discussed here. This type of maximum principle we can analytically solve this problem, and then the characterization of optimal control we can analytically find U1 star and U2 star, these two optimal control problem in this way. And now we can see in the numerical simulation, that is, this results agrees with our analytical solution. You can see without control, that is without any drug, our CD cell is going down very quickly and virus cell is rising up. But so it indicates that the treatment should be initiated at a earlier stage. Then in the right side, you can see when we use the treatment, that is the therapy, our CD cell is rising up and the virus cell is going down is very drastically. And when we use the control, that is our immunoboosting drugs and viral suppressing drugs, in the left side you can see our CD cell is rising, but our virus concentration after some days, that is after 30 days or after 10 days, the virus is again rising because of the resistance for the drugs. So multi-combination drugs should be applied. And in the right side, you can see immediately, you can follow our virus concentration. When we use the state variable, state constraint, then the virus cannot rise up at the state, that is 2.5. The virus can be halted at a minimum level using the antiretroviral therapy. And even you can see here, we consider initial condition is only 2, and it is also possible by using the highly active antiretroviral therapy at the initial stage, because it actually depends on the scheduling for the use of drugs as a multi-combination highly active antiretroviral therapy. So I have another application, but I think for the time consuming, for the time restriction, I cannot show all the details here. Just I apply another SCIR general model, general type of SCIR model, and the general type of SCIR model actually was developed by Susan E. Leonhardt, but he used a vaccination strategy, and when you can apply the vaccination, immediately the susceptible population should be recovered. And this is a very good strategy for using vaccination now, the present situation of pandemic, any pandemic disease or epidemic disease. But one thing Susan E. Leonhardt did, she used a isoperimetric constraint, but isoperimetric constraint is not realistic, because the supply, she considered that the supply of vaccine is limited. But that is, in that case, you cannot vaccinate all the people in a certain region. But we remove this isoperimetric constraint by using a state variable or a state constraint or mixed constraint. So using the mixed constraint and state constraint, we got very realistic results for this type of case. And in that case, you can vaccinate most of the population. In the case Susan E. Leonhardt did that, only 2,500 people can be vaccinated, but we show that about more than 7,000 or 8,000 population people can be vaccinated using the state constraint. So just result you can see, we modified these results and using the mixed constraint, and also another constraint also using here. The problem is the maximized, this is the mixed constraint problem. And another, we can use the state constraint model, and the state constraint model looks like this, as I discussed in our theoretical stage. And here is the maximum principal can be calculated using the pseudo Hamiltonian, and it is a mostly complicated, I already discussed, but the theory gives a very good unique results for the existence of the solution. And this is the characterization case, and we developed these results and good results. You can see here now the Susan E. Leonhardt, this results is only, you can see the vaccinated population. In the last vaccinated population only we can achieve 2,000 only 500, but and our susceptible population also is rising up. And in the case of the optimal vaccination therapy, you can see in the last slide figure that the vaccination is inactive after 5 or 7 years. But in our case, you can see if we use the mixed constraint, we can see that our vaccinated population can be maximized, and susceptible population also can be reduced. And optimal control strategy also is effective the whole duration of the program. And more good results we have achieved in the case of state constraint. You can see state constraint, if we restricted our susceptible population at a minimum level, then we can vaccinate the most of the people in the last of the program. That is 20 years of the program of the vaccination. and we can have a very good results for the optimal vaccination. And the whole period of time, first from the beginning, it is fully effective, and from the whole program of the schedule, the vaccination is fully effective, and we can have the a maximum number of population can be vaccinated. So this is the very unique results we can do it using by optimal control technique. So I would like to finish here because of the time restriction. So I think everybody have shared, and we can enjoy, we can share our research. So thank you everybody, and thank you all for your patience. I can have sharing.
Thank you, sir, for the precious knowledge that was indeed beneficial for understanding uncertainties in emerging disease. Now, let us take some questions from the audience. So the first question for you, sir, for HIV, how to have upper bound of viral concentration?
Yeah, it is actually very important question. Upper bound, we can put in bound. Actually, the bound represents our therapeutic treatment, because if we use the highly active antiretroviral therapy, so highly active antiretroviral therapy gives the virus concentration at a minimum level, and it actually depends on our scheduling for our doctors. So that we should work with our doctors. Then doctors can suggest how can we scheduling to use the drugs for the antiretroviral therapy, that is the multi-drug combination, and this multi-drug combination can give us a good results to stay at a minimum level of the virus concentration.
Okay. Any other questions from the audience? Questions are also welcome on live platform of Facebook.
Yeah.
So thank you, sir.
Thank you, everybody.
Yes. Thank you, sir. Now our next session will be carried on by Kanan ma'am.
Thank you, Puri ma'am. So we had a very great session from Biswas sir. Now for the second session for today, we have Professor C.S. Lalita ma'am. She's from Department of Mathematics, University of Delhi, South Campus. She has completed PhD from University of Delhi itself and has supervised many PhD and MPhil students in Department of Mathematics, University of Delhi. She is a recipient of prestigious INSA Teacher Award in 2016. C.S. Lalita ma'am has co-authored a book entitled Generalized Convexity, Non-Smooth Inequalities and Non-Smooth Optimization in 2013, published by CRC Press, and has co-edited 2 other books. She has published around 60 research papers in reputed journals and has organized many workshops and conferences, including the Indo-French UNESCO SIMPA School in 2013. Her topic for today is convex optimization and application. We welcome you, ma'am. You can please begin with the session. Hello.
Yes, madam, you are audible. Please share your screen.
Is my slide visible?
Yes, ma'am. It is visible, ma'am.
Slides are visible. Make it slideshow, madam.
Okay, I'll do that.
Click on from beginning. From beginning, left side, ma'am. The first option, ma'am. The first option from beginning.
From beginning. Left
yes.
side.
Left side, yes.
This one?
No, left side. That is okay. Then go to left side. Second menu, second left side. First one.
This one?
Below file, ma'am. The option is below file. from beginning. Left side corner below file from beginning.
Madam, icon which is exactly below file.
Below file.
Yeah.
Okay. Yeah.
Done. Done.
Okay.
So I am thankful to Professor Neeta Shah, Professor Falguni for inviting me for this conference. Actually, I have not been giving any presentations, but since I did not want to say no to Professor Neeta Shah, I agreed. Because of my busy schedule, I don't get much time. That is the reason. So I have kept my talk very, very elementary and something which is basic, and trying to see different problems or different concepts related to convex optimization and applications. So here my talk will be based on two things. One is convex sets and the other is convex functions and some problems associated with it. For first part, I'll be focusing on convex sets and some interesting problems associated with convex sets. And in the second part, we'll focus on convex functions and algorithms associated with solving convex optimization problem and an application in the end in medical imaging. So Professor Bishwas has also talked about an optimization problem. He talked about convex optimization under existence theorems and so on. So we may be trying to briefly touch upon those concepts as well. So convexity, as we know, is an area which is touching many other areas. So it can not be said that it's just a part of, say, discrete optimization or its optimization or its analysis. It's a part of analysis. It's in fact a multifaceted topic. There are many applications. There are many places where they occur. They occur in the area of functional analysis, calculus of variation, complex function theory of one or more variables. You can see that occurring in graph theory, crystallography, as well as optimization. So when we see this, we can say that it is a subset of geometry, it's a subset of analysis, it's a subset of discrete maths. So here it is lying, convexity. And of course, it's also part of some linear algebra, other areas, emerging areas which are occurring or which are being explored these days, or it is lying in the heart of many other areas. So if you understand that term convexity and not convex optimization, but convexity and convex functions, there are many connections which we have with various areas. One of the person who also talked about this is Dr. Victor Klee, who is famously known for his example on simplex, which shows that the simplex algorithm for linear programming does not work in polynomial time. So Victor Klee had given an example, a famous example, and also he is known for the art gallery problem. Let us see what he had to say. He said, the study of convex sets is a branch of analysis, geometry, linear algebra that has numerous connections with other areas of mathematics, and it also serves to unify many apparent diverse mathematical phenomena. So the importance or the unification through convexity is one aspect which we are considering today. So this definition of convexity of a set is very well known, and I'll just go through it. A set, we are only talking about in finite dimensional spaces. Of course, these things can carried over to infinite dimensional spaces as well. So let's say a set C is convex if for every x and y, the line segment joining x and y is in a set C. That is, if I talk about two elements in C, then the line, the convex combination of these 2 points, that is lambda varying between 0 and 1, also again lies in C. So this is very obvious. This is a convex set, whereas this is not a convex set, because if I take any 2 points and try to join them, then the line segment goes outside the set. So the first one is a convex set and the second one is not a convex set. So I'll just briefly say two few properties of convexity before going to the problems related with convex sets. One important thing is, if we have a family of convex sets, then the intersection is also a convex set. And and that is a very useful property, because when we are talking about solutions of a system of equations, say you have a family of equations and you have a solution and the solution sets are convex, we want a solution which is existing for the whole system, then you want that the intersection should be known. The nature of the intersection set should be known. And we know that if the CIs are convex, then the intersection is also a convex set, as illustrated by this figure. Also, another property is that if C and D are convex set, then their sum is also a convex set. If you see geometrically, if I have two sets C and D, and then we add them up, it is like this, it gets translated, decalculated at every point, and ultimately we arrive at the set C plus D, which is also a convex set. Another useful property is that a set is convex if and only if C plus C is 2C, which may not be true for a non-convex set, but C plus C is 2C. And if C and D are convex sets, they are into different spaces, Rn and Rm, then the inner product the product C cross D, which is a set in Rn plus M, is also a convex set. And if C is a non-empty convex set, then the closures and the interior are convex set. If I have a non-convex set, then it has an interesting property, that is, if a closure of C is closure of interior of C, which is not true in general. For example, if I see this apple, which is not a convex set, and this is a closed convex, it is a closed set. So C and closed C are same. If we take its interior, it is this, and when we take its closure, it is this, and you can see that closure of C is not equal to closure of interior of C. So this property, which is used, which can be used at many places, is not applicable or is not available in general, but only for convex sets. And similarly, we have interior of C is interior of closure of C. Okay. Now, then as we were talking about a system of equations, and then you want to have a non-empty, we have to have that, we know the nature of the set, that it's a convex set. Sometimes you want to find out whether you have a system of equations, whether it has a non-empty intersection or not. This is a very famous theorem which tells us that if I have a finite collection of convex sets, the number of convex sets may be more than 1 plus the dimension of the space. Say I'm talking about in R3, then if I have more than 4 sets, then I want to say under what condition is their intersection empty. Say we have 100 sets in R3, and whether the intersection of all the 100 sets is non-empty or not. The theorem says that if I take at the collection of any 4 sets, if every 4 set has a non-empty intersection, then the whole intersection is also having a non-empty intersection. So let's look at an example in R2 where we have taken 4 sets. The 4 sets are such that the intersection of any 3 set is non-empty. We can see there are 4 possibilities. The intersection of any 3 taken at a time is non-empty. Then the intersection of all the 4 taken together is again non-empty. Such a thing is not true if we have a non-convex set. For instance, if you see this example, this second figure, if you take any 3, say A, B, C, or A, D, C, or B, D, C, they are all non-empty intersection. But when we take all the 4 together, the intersection is empty. So this property, the Helly's theorem, may not be applicable, is not applicable for a non-convex set. It's only applicable for convex sets. Now I'm coming to some problems. One of the problem is the packing problem in 2D. What does this say? Suppose there are certain disks which are available to us in a 2-dimensional space. How compactly can we pack them up? Suppose you have seen in a honeycomb in nature, we have seen that how they are compactly packed. Let's try to understand that. Suppose we have certain disks, say they are all disks of unit radius, and we have to compactly arrange them. This is known that the compact arrangement is the hexagonal packing like this. This is the hexagonally, if you can compactly arrange them, and the constant, there is a called a spheric packing constant. What is the constant? Suppose you take an area, the total area of that square figure, suppose I know, and I know the area which is being covered, then what is the ratio of the area covered divided by total covered? Is it 80% is covered, or 100% is covered, or 70% is covered? For the circles, for the disk, it's known that the sphere packing constant can be calculated. How? Let's look at just the hexagonal portion. this hexagonal portion can be, so these circles are all of radius 1. So this hexagonal portion is comprising of 6 triangles, where each triangle is an equilateral triangle. The base of those triangles is of how much? 1 unit. 1 unit. So, yeah, 1 unit. So the area of that triangle will be 6 into half into root 3 by 2, which comes out to be 6 root 3. Half into 1 into root 3 into 2. That is the area of the triangle. So multiplied by 6, it is the 6 root 3. So the area which is covered by the hexagonal portion is 6 root 3. And in that hexagonal portion, you can see that 1 complete circle is there and 6 bits of circles are there. When we combine 3 bits, it forms 1 circle. So there are, in total, if we join them, there are 3 circles inside that hexagon. So the area covered is 3 pi, because 3 pi into r square. R is 1, so 3 pi. So what is the constant? The sphere packing constant is 3 pi divided by 6 root 3, which is approximately 90.69. So densest packing arrangement uses 90% of the space when we try to pack the space with circular disc. Now going further, so here we can see that these circles, discs are convex sets. So I have taken those examples from convex sets. There is another problem. If we extend this problem from 2D to 3D, what happens? Sir Walter Raleigh, he's a famous English writer of 16th century who was very close to Queen Elizabeth, and he was knighted in 1585. He had his assistant who was a mathematician, Thomas Harriot. So when they were going for some expedition, he was asking him, how can I calculate the number of cannons in a star? Being a mathematician, it was very easy for him to answer the question, and he solved the problem, and Walter Raleigh was impressed. But Thomas Harriot had a problem. This is okay. But what about this problem? What if what arrangement of the balls take up the least space? So when I'm talking about the balls, it's in the 3-dimensional space. How can you arrange them so that they takes the least space? So he had this problem in his mind and he could not solve it. So he consulted, that is like you have spheres, you can say oranges are there and you want to compactly pack them. So he went to his colleague, John Kepler, who is known for his Kepler's law of planetary orbits, and he raised this question to him. John Kepler did some experiments, and then he said that face-centered cubic pattern, which is a pattern favored by fruit sellers, is the best possible, and we cannot better this. That is this sort of packing. One sitting inside the gaps of the other. So this is the densest packing. He said that it cannot be better. So this was conjecture. So Kepler had conjectured in 1611. The proof could not be provided until 1988, when the advent of computational facilities with the introduction of high computers were invented. Like more computation could be done through computers. So one of the example is the famous 4-color problem. The proof was given in 1974 by Apple and Hacken, again using the computer. Similarly, this problem was ultimately proved, or he tried to prove in 1998. This is called Kepler's conjecture or sugar packing problem. In 1998, Thomas Hales found a computer-aided 250-page proof, and the referees were certain that 99% it is correct, but 100% checking these so huge computation which can be done on a computer, checking was not easy. So they said it's okay, it seems to be correct. This is Thomas Hales. Then in 2014, with the help of computer-assisted proof assistants, Isabel and H.O.L. Light, he ultimately gave the complete proof, and later it was published in Forum of Mathematics Pi. So let us see what is the sphere packing constant for the spheres. There are 2 possibilities, in fact. One is the face-centered cubic, other is the hexagonal close packing. In the first one, the first layer and the third layer are similar. They are placed similar. In the second case, there can be a little shift. So you can see that it's not exactly, the red is not, the green is not exactly above red. So both these packings are compact, and they give you the sphere packing constants to be, which I will not take up the complete proof. It comes out to be pi by 302, and this value is 74. That means the densest packing which is possible in spheres or in 3 dimension is that it takes 74% of the space in the box. That is the sphere packing constant from 90%, it has reduced to 74%. Now the question of course goes on that can we go on to a further higher dimension? It is not that easy, but recently the higher dimensional sphere packing has been proved by one of the female mathematician, Marina Vazokis, who proved that the sphere packing constants in dimension 8 and 2, and that too she could get it using the objects, which is the modular form, which is extensively studied by Srinivas Ramanujan. And this type of packing problems are useful because in communication technology, where they ensure that messages can be sent via internet, a satellite, or a telephone. So the higher dimensional packing comes naturally in that. But we know not much idea is there for other dimension, but for H and 24, the sphere packing constants have been found, and the sphere packing for dimension 8, E8 lattice packing sphere, this is shown to be 0.25. That means 25% of the space is used, and that means 25% of 8D space can be filled with non-overlapping spheres in 8-dimensional space. And for 24-dimensional space, which is called Leech lattice sphere packing, is known that the const it is 0.0019. So it is approximately 0.002. So it's that less. So as you go to the higher dimension, it becomes less and less. So more and more vacuum would be there, less and less space will be covered. Now, another type of solids, which are famously called Platonic solids, they are obtained by constructing regular polygon faces with same number of faces meeting at each vertex. There, it is known that there are only 5 types of Platonic solids. One is the tetrahedron, which has 4 faces, then the hexahedron, which has 6 faces, then the octahedron having 8 faces, dodecahedron having 12 faces, and icosahedron having 20 faces. These are also convex sets. So if I talk about the packing using these Platonic solids, it's clear that if we take hexahedron, we can completely fill our 3-dimensional space with 100% packing. The hexahedron will completely face the 100% packing because the whole space can be covered up. And then another possibility is that of tetrahedral, octahedral. That means you take a combination of tetrahedron and octahedron that can also completely pack. For example, if you look at this, this can be compactly fill up the whole spaces. So these are 2 possible spacing with Platonic solids. These are Platonic solids are also convex sets. So previously we talked about the spheres, and now we are talking about the Platonic solids in 3 dimension. The other problems, another concept which is associated is the star-shaped set. We know that a set is said to be star-shaped. If we have a figure like this, then you take a point X somewhere in X star. If that point can be connected with all the points of the set, then it is said to be star-shaped at X star. So in fact, the lighter portion in that star, every point in that region can be connected with every other point. So that is called the kernel of the star-shaped set. So this is the star-shaped set that all the points in the light portion can be connected with every other point in the set. So sometimes you can generalize the concept from convexity to star-shaped sets. The purpose of me giving this problem was just to give a glimpse of art gallery problem. The art gallery problem actual version was given by vector 3. We take a simpler version of that. It says that if for each, suppose you have this type of gallery, art gallery, where paintings are placed on every wall. And then there should be a person who has to keep, a guard should be there that these paintings are not mishandled. He should be able to keep a watch on all these paintings. Then the question is there a place where we can place that particular person who can keep a watch on all the walls? So you can see that this is something like the star-shaped set. So the art gallery problem says that art gallery is a star-shaped set. So it's actually the art gallery problem says if you have a large gallery, then what is the minimum number of guards required to keep a watch on all that? We are only talking about one guard. That is, there should be a star-shaped set, and we can place one guard at all these places. So this is the art gallery problem. Another problem is, can we talk about a body which has just one unstable and one stable equilibrium point? If we take this set and then try to adjust it, so these 2 points are points of stable equilibrium. That means if you just displace it, it will come and settle down here. These are stable equilibrium points, and these 2 points are unstable equilibrium points. So the question which arose is that, can we have a convex body with just one stable and one unstable equilibrium points? This is again an example of a roly-poly toy which is having a stability. If you just displace it, it comes back to its original problem. So this is the stability. So this is the question. This question was raised by Russian mathematician Arnold in 1999. Is this person? This question was raised. So there were interest, people started constructing, people started seeing whether they can find a solution or not. And ultimately 2 persons named Gabor and Peter, they were able to find out one. In fact, there is a story goes behind this, is that the Gabor tried to search for this type of body. He went to a beach, he talked and picked up all the pebbles. He tried to see if there is any pebble which is of that form. But ultimately, he said that I came to know many things about the pebble, but I could not find a body which has this type of existence. Later on, these 2 persons were ultimately able to find out an object, and they call that object as Geombo, Geombo, and this is the object which they created. And there is one which is there at Corvin, it is at Budapest, Hungary. In fact, there is one at Cambridge University also where they have donated one, and there is a site where they sell this item. So this is a hot item which is being sold, and as this is being given as a memento to mathematicians going to a conference and so on, because this is a very treasured object. And to make it, they have created a website where these things are available in various material, maybe in glass, metal, and so on. So these things are available. So this is again a problem which was associated with the convex set. And I come to the last good part of this convex set. This is a happy ending problem. Suppose the question is, if I am in R2, by a general position, I mean R2, 3 points, if they lie in a line, then they are not in general position. So that means if I am in R2, hyperplane is of dimension R2 plus 1, 3. So 3 points should not lie in a set, in a collinear. 3 of the points are not collinear. So you can see these 4 points are not collinear. The question is, given 4 points which are not in general position, can they always form a quadrilateral? The answer is no. Here, of course, they form a quadrilateral, but if the positions are like this, then I cannot join all of them and to form a quadrilateral. I don't get a quadrilateral. However you try to join, it will not be a convex. It should be convex quadrilateral, not a quadrilateral convex set. It cannot be a convex set. So what is the problem? But if I take 5 points, however you place it, that's such that no 3 of them are collinear, we can always find a pair of 4 points which will form a convex set, convex quadrilateral. This is the problem. Any set of 5 points in a plane in general position has a subset of 4 points that form the vertices of a convex quadrilateral. Convexity is important here. So actually, this problem was solved by 2 persons, George and Esther, and they were involved in this problem. And ultimately, after their solution, they got married and they lived a long life and also died on the same day. So this problem was actually termed as happy ending problem by Paul Erdos, just because this ultimately led to their marriage. So that is why this problem is called happy ending problem. And the same question can be there if I have, say, I have to make a convex pentagon with 5 points. 5 pentagon has to be made. Then how many points should be there? There should be 9 points. Convex pentagon requires 9 points, and a convex hexagon actually requires 17 points. But the proof for 4 points, 5 points was given by George and Esther. So that is again a problem associated with convexity. Now this part is over. Now I go on to the convex sets. So if we talk about the importance of convex sets, we just recall two persons who have talked about this. One is the Jensen in long back. According to him, convex functions plays a great role as similar to a positive function or an increasing function. It should preserve an important position in literature. Later on, this is a famous person, Terry Rockefeller, who is the author of the classic book Convex Analysis, or you can sometimes call him as the father of convex analysis, convex functions. He also said that the greatest watershed in optimization isn't between linearity and non-linearity, but convexity and non-convexity. And those of us who work in optimization, they know that treating or regarding a convex problem is much more different or easier in comparison with treating or dealing with a non-convex problem. So the distinction is obvious. Convexity is the first stepping stone, and to go to non-convexity, we have to do all the possible tricks. It is not that easy, but for convexity, everything is well defined, like in linear programming. Now, the definition of convex function, most of us know it. So this is a convex function, f of 1 minus lambda x plus lambda y. So I don't go into the detail. This is self-explanatory. That means if I join any 2 points on the curve should lie below the line segment joining them. So some of the examples are, one is very simple example, x square. You talk about e to the power of x, it's a convex function. You talk about a affine function, it is a convex function. If you go on to 3 dimension, this x square is a convex function. If you go on to x square plus y square, it's again a convex function. If we talk about under root of x square plus y square, this is a convex function. So all of them are convex function. It can be given in higher dimension as well. So the property, which is one of the property which can be shown about the minimizers and local minimizers, is that a point is a minimizer if fx star is less than equal to fx for all x belong to M, for all x belong to the domain, and it's a local minimizer if such a thing happens in a neighborhood around x star. So in this figure, we can say that this figure, it is defined on the set AB, the function, a real valued function defined on the interval AB. We can say that x star is a local minimizer, y star is also a local minimizer. Actually, it also happens to be a global minimizer, and the A is also a local minimizer, because we have, if I take the neighborhood around A, we have to take only points of C of the domain of the set, which is C which is the closed interval AB. A is also a local minimizer, whereas the global minimizer is y star. And you can see that this function is not convex. So what is the appropriate thing in convexity is that if we have a convex function, then such a thing will not happen, that you can have a local minimizer which is not a global minimizer. So that means whenever we have a convex function, local minimizer is a global minimizer. That is what is the catching point when we develop the algorithms. Even if we strike at a point which is local minimizer or a stationary point, we are so happy because the function being convex, the point itself will be a global minimizer. When you come to the characterization of convex functions in differentiable case, I'll just come to the characterization. This is the characterization. Geometrically, what it means is that if we talk about the tangent plane at any point on the curve, that the tangent plane will always lie below the graph of f. For example, if we have a curve which is differentiable convex function and try to draw the curve, draw the tangent at any point, the tangent will always be lying below the curve. If you look at this in a for a 3-dimensional case, let me say I have this function y1 square plus y2 square. This is the function, and we're talking about the tangent plane at 1, 1. That means we want to illustrate the above theorem for x is equal to 1, 1. The function which I have to take is the one which is available on the right-hand side, which is a function of u, x being fixed. Then the function g is coming out to be, what is the function? This is the function g, y1, y2 is this function. And you can see that this function lies below this. And if you want to see it in a different angle, it is just touching the curve at one point. So this is true for every point. So tangent planes are only going to touch it and it is going to lie below the curve. This is also useful at many places. Now, this gives us the important property that a stationary point of a differentiable convex function is a minimizer. That is, if gradient of fx star is 0, then we can see that fu is greater than equal to fx star for all you belong to C. That means every stationary point is a global minimizer in the case of a convex function. Now, this problem was a general version was considered by Professor Vishwas. I just consider the problem minimizing fx subject to x belongs to C, where C is a convex set and f is defined an open convex set containing C. Let us look at this problem as he was talking. Here we can have the contours. You draw the contours of this by cutting sections of this paraboloid. Then you will have these types of sections and find out the smallest section contour, which is going to go and touch the curve. And this point, it will go and touch at this point, and this point is half The solution of this problem is half. Now, what is the advantage of convex optimization is that well-defined techniques or solution is there. One of the technique is if you have to minimize a function subject to x belongs to C, the gradient method consists of two steps. I'm not going into the literature, I'm just giving you the idea. The two steps involved are you start with the feasible point, identify the direction of descent, in which direction should I move so that the value of the objective function improves, and then find out how far I have to move. That is to calculate the step length. For example, if this is the convex set and have a point x0, the question is which direction should I move? Suppose I found out the direction happens to be steepest descent, luckily happens to be simply d is minus of gradient of fx0. So if I know the objective function, I know the direction is not a problem. So we move along the problem, and then the question is how far should I move? That is the step length. And luckily there is another thing. If delta f is known, if suppose the gradient of f is Lipschitzian and the Lipschitzian constant is L, then the step length is known to be 1 by L. So the algorithm is simply x0, x1. This is a very basic raw algorithm. There have been lots of modifications. I'm just saying the simple technique. x1 is equal to x0 plus 1 by L minus gradient of fx0. So we have this algorithm. So based on this, sometimes it's also called convex simplex method, the solutions are given for a convex optimization problem. Now the question, I'm coming towards the end, where we have to talk about an application in CT scan. So what is a CT scan? It is, many of us have seen the CT scan, where there is a person which he lies on a bed and he's taken inside the CT scan, and then certain X-rays are passed over the set, and this round structure keeps on moving. So it collects the two-dimensional images and on the other side, and then from those we have to construct the three-dimensional structure and then predict whether there is any problem internally. That means it's some sort of imaging without actually cutting down the body. So this is a medical imaging CT scan. Now let's look at what is the governing idea in CT scan. What is the equation, and then try to see how to solve it, and then using the algebraic equation, and then finally by optimization method. Suppose you assume that X-rays are moving along a straight line. When it moves through the body, X-rays will be absorbed by the body. Initially, suppose I have some amount, say I0. As it goes through the body, I0 keeps on decreasing, and when X-ray comes out of my body, it will be final intensity, I say IF. So it depends on the distance covered. So it is a function of S. As S increases, IS decreases as the X-rays are absorbed. So if X-rays have traveled through a distance delta S, its intensity is reduced by a small amount delta I. So this reduction depends on two things. Optical density, if it is a very dense body, more absorption. If it is a very, suppose it is passing through my bone, more things will be absorbed. If it is just passing through the tissues, cartilage, it will be less absorbed. So it depends on the density of the material. So what is the governing differential equation? A gradient. Yeah, I just complete in 5 minutes.
Thank you, ma'am.
Okay. Gradient delta I is minus US IS delta S. So this is the differential equations. And if you look, initial velocity is I0, final velocity is IF. This is the differential equation, a simple first order differential equation. Anybody can solve it. And this is the solution, which implies that this is the value. So if you look at this value, IF is known to me. I can measure what is the intensity after leaving the body. I0 is known, so we know R. What is unknown? US is unknown. So the problem is when you have this differential equation, the solution of the differential equation R equal to integral US ds, R is known to me, I want to calculate US. So if we have, this is what is exactly done in CT scan. So inverse Redon, this is called a Redon transform, inverse Redon transform can solve the solution, which is of course not easy. So how is it usually done? It is done through discretization. That is, suppose you have to solve it, this one we discretize. Discretize means say I make it into discrete points. Say we have these pixels. Suppose some rays are passing through an area and they have the pixels are represented by index ij. So there are 4 pixels here, and T is the set of indices over the pixel area. Aij is the proportion of the area traversed by X-ray at pixel ij. Then, so there are 4 areas, A11, A12, A21, A22. Uij is the density of the pixel. So my problem is ultimately to find out Uij. How do I find out Uij? So the discretized version of the above relation is R double, which is the summation, double summation over ij belong to T. So my US I have represented by Uij, and DS, the length we have discretized into area, so Aij. So we know Aij, we know R, we do not know Uij. So it is simply reducing to a system of equations. For example, if we have this ray, let us say an area curve has passed like this. So this particular ray is completely covering A11 and A12. So the equation governing will be R1 is equal to U11 plus U12, because the complete area of A11 and U12, because it's actually 1 times U11 plus 1 times U12. Let us look at the second one. It gives me R2 equal to U21 plus U22. Suppose you have a vertical ray like this, it is R3 equal to U11 plus U21. Suppose I have this. So this particular area, the curve, the one which is passing, let us say it is only covering 2/3 of this area and 1/3 of A12 and 1/3 of A21, and it is passing through 2/3 of A22. Then the governing equation is this, R4 is equal to this. So what is a system of equations? This is simply a system of equations. So if we can solve this, if I know the inverse of the system of equation, I can find the value. So it is ultimately reducing to solving a system of algebraic equations. So anybody who has a good knowledge or good application or good computer software to solve a system of equation can get a fairly good picture of the points inside our body, or we can reconstruct what is there inside our body. So this is what is being done in the medical imaging. Now the question is, how can this problem be solved in optimization? In convex optimization, if we have a system of equations, simply say y equal to ax, and I have to solve it by convex optimization. We just minimize this function, minimize fx subject to norm of y minus ax square subject to x belongs to Rn. What is this? Solution of this is simply solution of this. So this is a convex optimization. So if I know the methods to solve a convex optimization, one of the methods I have illustrated. So simply converting into convex optimization and solving gives us the solution. So these are the things which I just wanted to convert, ending with an optimization application. So many of the sources, the recent one I've taken from math+org or some other math new items. And for the other areas of convex sets and convexation, these are some of the books or some of the books on convex sets and convex applications. So I come to the end of my talk. Thank you for your patient hearing.
Thank you, ma'am. Any questions we have? Any questions? If anyone has, then they can write in the chat box.
I think on Facebook, 6 hands. On Facebook, 6 participants raise their hand if they have given questions.
Madam Jitendra is typing in the chat box the questions which has been asked in the Facebook.
Okay.
Okay. Okay, so I think that one question was already answered, and okay. So ma'am, we have a question that how we check whether a transportation problem is convex or not.
Transportation problem is a linear programming problem, and every linear function is a convex function. So it's obviously a convex optimization problem. Every linear optimization comes under the class of convex optimization.
Thank you, ma'am. Sir, do we have any other question? Okay, I think so. There is only one question here. Thank you so much, ma'am. That was undoubtedly a very wonderful session, and absolutely with facts and fundamentals. And together with that, we came to know about the history a little bit, especially the happy ending problem. Thank you so much, ma'am.
Thank
Let
you.
us-
I think I finished much before time.
Yes, ma'am. Yes.
Thank you for giving me time. Thank you.
Thank you, ma'am. Thank you so much. So for the next session, we will be having with us Professor Neeta Ed Shah from Department of Mathematics, Gujarat University, India. Professor Neeta ma'am has PhD in statistics from Gujarat University. She is postdoctoral visiting research fellow of University of New Brunswick, Canada. She has published 13 monographs, 5 textbooks, and over 475 peer-reviewed research papers, and has completed 3 UGC-sponsored projects. She has guided 28 PhD students and 15 MPhil students till now. 8 students are pursuing PhD and 1 postdoctoral fellow too. She has received Best PhD Guide Award from AIMS 2019 and Best Paper Award from Gujarat Science Congress 2020. She is a Vice President of Operational Research Society of India and a Council member of Indian Mathematical Society. She is also a President of Operational Research Society, Ahmedabad Chapter. We welcome you, ma'am. Her topic today is Global Stability through Graph Theory for Digital Learning. Ma'am, you can begin your session, please.
Thank you, Kanan. First, let me share. Can you see my screen?
Yes, ma'am. Yes, ma'am.
Okay. So I'm touching a topic which has arisen due to pandemic COVID-19, and that is about digital learning. So when digital learning will get stabilized, that is what myself and my team, research team, was studying. So topic of my title is Global Stability through Graph Theory for Digital Learning. We are organizing this conference, as already said in inaugural session, that Digital International Conference on Applied Mathematical Sciences. So there is myth that applied and pure maths are totally different. But here, this is an attempt that once I know concepts of pure mathematics, then only I can apply it on the live problem. So here we are going to have graph theory to know the global stability of the issue which has arisen due to COVID-19. Research team is Purvi Pandya and Ekta Jaiswal. Ekta Jaiswal is getting a fellowship from the Prime Minister fellowship program, and Purvi Pandya is getting fellowship from the South Gujarat State Education Department. So we have, just a minute, I just want to reduce this. Okay. So technology plays an immense role in every walk of human life, whether it is a transportation, education, healthcare, or communication. Every advancement in technology, it is becoming an alarmingly urgent question that necessitates the investigation of their negative impact. For example, if we take negative part of the transportation, most of us are using car to reach to our destination. Okay, but in that case, we have reduced our walking. And for that, you need to go for walking in morning or evening. Okay. Education, we will see. Healthcare, negative part is, even though COVID-19 patients are getting recovered, but they have side effects, that what has been said in last week, that COVID is medical treatment given by the, taken by the same patients. In fact, other normal scenarios of the vital bodies. Communication we'll talk about here only. So innovation such as digital learning has become, just a minute, has become ubiquitous in students' life. We are more concentrated on students' life, which encompasses of internet facilities and a huge collection of apps. The use of such facilities differs accordingly in various age groups, students. So we are talking about kids, that is playgroup students, even they have to go for the online classes. And our college students, they are also going for the online classes. And also the symptoms and the risk attributed to addiction of digital learning use may differ during various learning stages. We'll see various stages also. This has proved to be a greater risk physically, mentally, as well as socially. Physically, in the sense, a student is sitting for almost 6 hours to have an online class. For 6 hours, he is getting knowledge and knowledge. So his mental status also gets slightly damaged. Slightly damaged means he has to concentrate. If he doesn't concentrate, then he will lose some of the things. And socially, obviously, when student or when anybody remains associated with internet for 6 to 8 hours, that means you got socially detached from even from the family members. The risks are in terms of emotional, mental, or psychological, such as mood disorder, sleep disorders, depression, isolation from the society, anxiety, physical like obesity, back and neck problems, and many social problems. On this, we have seen in the film industry, like many of the actors went in depression, they suicide also because they got isolated from the film industry. Okay? That has changed their order, and at last they did suicide. Or some of the people went for drug addicting because they were not knowing what is the direction where they will be going once this pandemic gets over. Obesity, we already know that if you sit for 24 hours, starting from March 22nd till today, then obviously weight will increase because you will have food regularly and obesity will increase. But when you are at internet, your back and neck is getting stress and you will have problems. Many more analyses and surveys are done to study the positive as well as negative impact of digital learning. Positive use of digital learning among students can be seen where it encourages them in learning process, stimulates the mind, feeling, also gives positive values and breeds media literacy among them. So we are asking students to go for the online lecture and asking them to get engaged in some or the other thing. So that is a positive impact. Also, digital learning applications such as WhatsApp and Facebook are proved to be great help for online learning. Today, this conference is Facebook Live. So even if participant has not registered, they can learn a lot from all our 8 lectures. Digital learning has affected a lot as parents are busy working or they themselves are addicted to digital learning and don't have enough time to take care of the children. So this is, one can say, socially, children and wards and parents are getting detached socially. A model of digital learning of early childhood consisting of antecedents as parents and child variables and consequences referring to mental and physical development is analyzed. A study to understand both positive as well as negative impact of this digital learning on education or business or health sector or human psychology or social life was conducted, and the results with recommended solution to reduce negative impact on society was concluded. So if you think about positive part of digital learning, particularly in COVID-19 phase, we all are getting engaged because of online learning. So that is a positive impact. Additionally, the health issues prevailing due to digital learning were found and studied. Issues such as stress related to academic performance and satisfaction with life anxiety and family relations, social anxiety, and loneliness. These are the issues which are considered to be the negative one, and they are increased also. Number of times being a professional in academic, we get a phone call that we used to have, we were thinking of getting a university first in this particular exam. And if we go with the new exam system, then we don't think that we will get university rank. So students are more worried about academic performance. The overall impact of digital learnings on health and life is assessed here. To save students from the risk of such health issues, self-regulating mobile apps was proved to be very useful according to survey taken from 284 college students. This survey was done by someone else. We have not done. We have taken data from it. Also, joining different programs to reduce digital learning over-dependence and improve peer relationship and self-efficacy. Now, digital learning also increases self-efficacy because student will able to find out the way in which he will able to understand in a better way. There are huge number of literature is available, so we can find out using the data and get the clarity. People enjoy great comfort with the advancement in the technology. As we said, it is digital learning. So to scrutinize the rate of health impacts due to addiction, because now one can say addiction only, addiction of digital learning use, whether it is a positive or negative, we are going to talk about. So here we have compartmental model consists of 6 rooms. One can say compartments or rooms. First one is the student who are infected with digital learning, then expose, then whether infection is positive, infection in the sense whether digital learning is taken as a positive sense or negative sense. IN stands for negative. Then health issues comes, one has to go for medication. So this is compartmental model, and arrows represents directions in which individuals are moving towards. V is the recruitment rate, mu is mortality rate. Mortality rate here is considered to be, for example, if I say infected with positive or infected with negatively, if mu I take, that means I'm neither infected positively, I neither infected negatively. That is, I remain neutral in my learning. Okay? And alphas are the rates at which student will move from one room to the other room. So we have 6 compartments, and now we need to find out, this is natural birth rate. If you want, you can say rate at which student gets exposed to digital learning use. Then alpha 2 is rate of exposed students get positively infected. Similarly, alpha 3 is negatively infected. Alpha 4 is rate at which positively infected individual move towards negatively infected. So with some advice from the parent side, positively infected student can move to the negatively infected. Similarly, alpha 5 is those who are negatively infected can move to positively infected. Alpha 6 is positively infected gets health issue. Similarly, alpha 7 is negatively gets health issues, but both of them will have to go for the medication, because for sitting for the 6 hours on the same chair gives pain not only to neck portion, but it also gives stress to the spines, and lower portion of spine may get damaged. Okay. Alpha 9 is the rate at which after medication, obviously because of the pressure of the examination, they will move to exposed class once again for the digital learning use. So now I can define how this, I said this is the rate at which one individual moves from one room to the another room. So we have our differential equation tool and it is considered in a continuous case. So I can define what is the rate of change of student who is infected moves towards the other classes. So here is the first component. Second one is the rate of change of exposed, and one can see that they are either in SI or in positively infected, negatively infected, or they can go directly to the medication, or they are removed from the exposed. Similarly, rate of change of positively infected, rate of change of negatively infected from the both infected individuals or students, what is the rate at which students will be having or getting health issues and how many goes for medication. So now I have 6 differential equations. So we have set of, or I can say system of differential equation, which we need to solve. Now, first step, once you have a system of differential equation, is to get the equilibrium point. To get equilibrium point, just set all the rates to be equal to 0. That is what we do even in classical optimization. To get stationary point, we equate first derivative to be equal to 0. So equating first derivative to be equal to 0, I am having 2 equilibrium points. One is y0, that is digital learning free point. Don't go for any digital learning, and live life happily, keeping books aside, keeping learning aside. And another one is optimal digit learning point that we in epidemiology science, we call it endemic point. And why it is an endemic point? Because there will always be some optimum number of individuals in each room. That is, some will have medical issues, some will have to go for health, who are infected either by positively or negatively digital learning, and so on. So we once I know system of differential equation, first point is to get the equilibrium point, which can be obtained by setting system to be equal to 0. Then to study the spread of the addiction among individuals, we need to find out basic reproduction number. This is called a threshold or optimum value using next generation matrix method. This reproduction number gives the percentage of individuals susceptible to digital learning use and who may get addicted or infected over a period of time. It is in general denoted by R0, and here we have expression of R0. I will give you value of R0 also once all constants are known to us. So here it is. We have taken this constants, this rate from the paper, and it says that one infected, that is one who uses digital learning, infects 3.49. That is, an individual can make 3 other individuals susceptible to digital learning use and also make them addicted to it. Best example is nowadays we are getting announcements of international or national webinars every day, almost 4 to 5. Okay, and that means if one person has attended one program, then he will ask 3 more groups or 3 more individuals that we can get some knowledge about the research going on or recent research which is prevailing. That is what is reproduction number here. Let us have global stability. For that, I need to have some results from the out degree and from graph theory. First one is out degree, written as D plus. That is the number of arcs or arrows directed away from the vertex I. That is from one room to another room, okay, which is going away. And the number of arcs or arrows directed towards the vertex, is known as in degree. That is what's one which comes in, it is called in degree. Then Kirchhoff's matrix tree theorem says for n greater than equal to 2, we have Ci as the cofactor of Lii in L. L is the graphical representation. Then I can get Ci, and Ti is the set of all spanning tree T of a graph GA, or you can say GV, that are rooted at the vertex I. Moreover, if GA is strongly connected, then all this Ci, that is cofactor value, will turn out to be positive for each I, that is for each vertex. Then lemma says, let Ci be given in as given in the Kirchhoff's matrix tree theorem. If Aij is greater than 0, Aij are the weights, and degree, out degree is 1 for some I, then I can find out what is Ci Aij, and it can be worked out using the summation notation. Secondly, assume Ci to be as given in the Kirchhoff matrix tree theorem, and we are talking about the out degree, in degree, sorry. In degree is 1, then I can find out constant Ci Aij, that is what should be the weight given to the particular age is given by this constant formula. So result says I can apply, if these assumptions are satisfied, there exists a function Vi from U to say graph G, and Gij from U to something, say X, and Aij is greater than 0, then I can find out Vi dash, that is new vertices, using this. And if M is matrix Aij, each directed cycle C of graph GV and has this quantity less than or equal to 0 for each X in U, where epsilon C denotes the arc set of the directed cycle C, then the function Vx with this constant will satisfy certain condition, and that condition is V dash, that is derivative of the function is less than or equal to 0, and actually this function V is nothing but the Lipnow function for the system, and this function is already defined by Professor Biswas in the first lecture. I'm simply using it in the terms of graphical theory. Now, using graphic theoretical results for global stability, I have created functions Vt and Vid, V for vertices. We had 6 compartments, so there are 6 vertices, and they have been created using vertex, using the optimal value of the each compartment and with compartment and this function, log function. Then you different, because I had to say that derivatives with first derivatives will be less than or equal to 0. So we are differentiating each one with respect to t, that is v1 dash, v2 dash, and so on. Everything is worked out. And now I'm ready to plot the graph. I have the 6 vertices, 1, 2, 3, 4, 5, 6, and A1, A21, A32, A53, and these are the weights, you can say, or values which are given by the formulas which has been said earlier. Here you can find good number of cycles because the result says cycles should be there. Here you can find good number of cycles. For example, I have one cycle, say G43 plus G34 equal to 0. Just for the illustration, I've taken one cycle, but you can have good number of cycles. Even I have G32 plus G53 plus G65 plus G26 equal to 0. And try to find out many more cycles. Just a minute. Now I will have to move this slightly below. Okay. So once again, I'm plotting that. Now here for first one, what is outward degree? That is outward degree of vertex 1 is 1 because there is only one arrow going away from it. So I have C1, A21 equal to 0. So I can find out what is constant C1. Similarly, for find out out degree for each vertex, D5, D6, D5 plus D6 plus, I'm getting constant C6, C2, and so on. Similarly for C2, C6, and if you combine all this, we have V dash less than or equal to 0 if and only if the endemic point, that is optimum value, coincides with the initial points. So this proves that Y star is This proves that Y star is only variant set in interior of the set, indicates that Y star is globally asymptotically stable. Now let us see the results. Here we have color and write-up is matched together. Pandemic COVID-19 forced students to go online learning by the educational institutes. Now red color says students may not understand what is taught online and deviate to use other entertaining tools like games. That is the negatively one. Now here we can see that at an early stage, that is approximately, this is talking about the playgroup students, 3 years of age, children easily get exposed and are negatively infected, which leads to the different health issues. Not only health issues, even education issues. He may not be able to understand what is going on in the class. Moreover, for some cases, it is noted that these negatively infected individuals, after a period of time, may use digital learning positively. Once they come to know that we have to go with it, so they start doing it positively, and vice versa. Also, after procuring medication, approximately 55% individuals again get negatively infected. Here, procuring medication is in the sense either by the parents itself or by the psychiatry, not to go for something else instead of going for the positive learning. So they do come back by 55%. Now here we have directed graph. It says that the direction of exposed to medication. It says the behavior change of individuals in the respective compartment, and compartment, as I said, I have that of exposed and medication. The intensity of exposed individuals to digital learning use decreases if they procure medication in terms of limiting excessive phone usage. If doctor is advising to use phone or digital learning only for some hours, obviously it has to decrease. So limiting excessive phone use and involving them more in other fruitful activities. That means not outside activities, but at home also they can do some other productive activities. Now here I have hospitalization and medication. Obviously, individuals suffering from health issues due to addiction stabilizes if they procure proper medication. And that is quite obvious for not only for digital learning, for any medical issues. So it says that 26% individuals susceptible to digital learning use, 19% gets exposed overall. But out of that, overall 11% are positively infected and 21% are negatively infected. So almost 22% are moving towards the negative learning. Negative learning is, even this happens in our class. Not necessary that all the 100% students are paying attention to the classes. And once they get infected, they go for hospitalization, and it says that 11% suffers from different health issues. But yes, even positive side is that 12% can come out from the particular health issue and go back to the digital learning. Further, if we compare only infection and hospital issue, we see that 25% positively infected and 49% negatively infected. But because medication is costing high, even you are not supposed to go out, so only 26%, not only 26% suffer from health issues. So as a overall, what we concluded, that is Purvi Pandya and Ekta Jaiswal with me. During the COVID-19 pandemic, quarantine or work from home was imposed for the safety of individual, which led to increase the use of digital learning. A systematic pathway we use to design mathematical model where individuals susceptible to digital learning use get exposed and may get positively or negatively infected. No doubt this is not in your hand whether particular individual is getting infected positively or negatively, but because he has to kill a time, due to which they may suffer from different physical and mental health issues, but they can recover if they go for the medication. And as I said, that this system said that one individual will expose to 3 more, or I can say even 4 individuals for digital learning. And graph theory, we proved that the system is globally asymptotically stable. There are several ways that can help to control and minimize negative impact of digital learning use in the society by educating users on how to use it smartly. And that is also going on from state governments, that digital learning should not be for more than 3 hours for a particular age of group, and many more, and engaging themselves in other activities which do not rely on technology. Obviously, you need to ask your ward to go for some other activity which doesn't require laptop or internet or mobile. So we have evolution of man learning from illiteracy to mobile. And that is what me and my team wanted to say. Thank you. This is from my end.
Do we have any questions?
Yeah, there seems to be 7.
Yes, ma'am. I'm just reading from the chat box. Ma'am, there are so many feedbacks from the participants. Piyu sir is saying that excellent explanation, very informative session. Do we have any questions? Any questions from the participants?
Rajarani madam, any question? Professor Bhargav? Unmute yourself. Unmute yourself. Madam, unmute yourself. Unmute yourself.
Thank you. Thank you. I was to say it's so wonderful. You know, it's not my subject, but I enjoyed thoroughly.
Thank you.
Wonderful,
Thank you.
Wonderful, wonderful.
Madam, many of them have not gone through it. It may not be the topic, but at least they will come to know that there are applications everywhere of mathematics. And that is
true.
what we wanted to do.
Yeah, that's what I also try to do in smart materials.
Yeah, it was a wonderful experience, Professor Neeta Shah, hearing you.
Thank you, madam. Thank you. Thank you.
So nice, so nice.
Thank you, ma'am. Madam, it was a wonderful session. As everybody said, that was a novel topic actually, and new dimensions might have opened for the viewers for their future research papers, as well as those who are aspiring for such kind of research on the recent trend we are facing and the recent changes we are facing. Thank you so much, ma'am, for this wonderful session. Thank you, ma'am. So next session will be talked through by Purvi ma'am. Purvi ma'am?
Yes, ma'am. Yes, ma'am. For this session, we have Colonel. Yes,
Dimple sir is joining within 5 minutes.
Okay.
Hello, Dr. Falguni.
Yes, ma'am. How are you?
How are you? So nice to see you. Fine. Yeah, that's good. What's your basic subject?
Madam, I have done my PhD that is on mathematical control theory.
Okay. You are lecturing, no?
Yeah.
No, oh, that's wonderful. I will. It's probably tomorrow.
Yes, ma'am.
Okay.
My lecture is not there over here.
Then where are you talking?
I am convener along with Neeta madam in this conference.
Okay, that I know. That I know.
Okay, fine.
Okay, yeah, okay, so nice. Nice talking to you.
Same here, ma'am. Thank you.
Neeta ma'am, we have many people who has written very appreciative comments for the session in the chat box.
Thank you. Thank you.
If you want to say something, yeah.
No, thank you. I said everything. So now nothing more to say. Thank you all. Thank you all.
Yes, I think he's here.
Madam,
Yes, ma'am.
Dimple sir is with us.
Yes, ma'am. Yes, ma'am. So for this session, we have Colonel Dimple Kumar Chalisuja, Professor of Applied Mathematics at Virginia Military Institute, Virginia, USA. Colonel Dimple Kumar is conferred with PhD from the Indian Institute of Science, Bangalore, and University of Baroda, Vadodara, India. With over 24 years of teaching experience at university level, he has 55 research publications in peer-reviewed international journals, more than 63 presentations in the conferences, including invited talks with one monogram editorial board of 11 journals and reviewer of 25 plus journals. He has reviewed more than 125 research articles for peer review journals and has guided 4 students for PhD course, 15 students for graduate and undergraduate level independent research. Today's topic is optimal control for fractional stochastic interro differential. We welcome you, sir. And now I would like to request him to begin with his presentation.
Thank you, Ms. Purvi. Can you hear me, guys?
Yes, sir. Yes, sir.
Okay. Thank you so much for the introduction, and thank you so much, the convener, Professor Neeta Ed Shah, Professor Falguni Acharya. Thanks for the invite. Yeah, so without wasting time, I just would like to start with my topic. So today I'm going to talk about the optimal controllability for the fractional stochastic integral differential system driven by the Rosenblatt process with the Poisson sum. So first of all, I just would like to let you know that how this title is justified, and then after I submitted this article to JOTA, and we had to and for lots of communications with the reviewers, and finally that article is accepted for the publication. So that's what I just would like to share with you. So first, here I'm going to give you the introduction portion. That's what I told you, that how this title is justified, and then after some preliminaries, and then after the existence and uniqueness of the problem with the optimal controllability. And finally, the applications will be provided with some conclusion. I mean to say, what is the future work? One can extend the work based on this work. So let me start with this one. We know about the fractional differential equation because since last 5-6 years, or I would say almost 7 to 8 years, people are diverted to fractional controllability or fractional differential equation, fractional stochastic differential equation like this. So fractional differential equation is about to generalization of the integer order and derivative to arbitrary order. And lots of potential applications are there based on the fluid flow, electrical network and control theory, etc. And people have been working in this field, in the application field, since last 5-6 years too. And then after, you know that we want the our system that will contain the Poisson sum. So let me just introduce what we mean by the Poisson sum. So many real life situations can be modeled by the Poisson sum. Using the Poisson sum, as per example, the system jumps from the normal state to another state. The strength of the system is random. And in order to make more realistic jump model, the jump term is included in any dynamical system. And again, people have used this jump term and try to extend their work. And these are a few of the references. Here, the main theme is the difference between the fractional Brownian motion, Wiener-Ito integral, and the Rosenblatt process. So that's why I just would like to let you know about this thing too. So what we mean by the fractional Brownian motion. So fractional Brownian motion are utilized largely due to its self-similarity, stationary increments, and the long-range dependence for the long-range dependence. Tudor is the main author because I prepared this talk using this book of Tudor and a couple of papers of Tudor. So he investigated some properties of the Rosenblatt process with self-similarity process with stationary increments and appears as limit of the long-range dependent stationary series in the non-central limit theorem. And then after this, Tudor and his student, they extended, they have actually proved some of the properties, they have developed some of the properties of the Rosenblatt process. And then after San and Rand, they obtained some set of conditions, of course, a sufficient condition for the existence of the solution of some neutral stochastic partial differential equations using this Rosenblatt process. So that's how the work has been extended. And here we are going to learn about the optimal controllability. So very frequently, the optimal control is largely applied to biomedicine, in particular to model the cancer chemotherapy, and recently applied to epidemiology models and the medicines. And the main goal of optimal control is to find an open loop control, the optimal values of the control variables for the dynamical system, which maximizes or minimizes the given performance index. And if that fractional differential equation describes the performance index and the system dynamics, then the optimal control problem that is known as the fractional optimal control problem. And people have been working in that direction too. Some of the references are over here. So motivated by this aforementioned research work, here in this talk, we are going to discuss about the sufficient condition for the existence of the solution of the following class of optimal control problems: stochastic integral differential system driven by the Rosenblatt process with Poisson jump. And that problem that is given in this form. So this is the system, and let me first explain to you about the system components. So this is nothing but the Caputo derivative. Caputo derivative C d to the power alpha xt. Caputo derivative of order alpha is lying between 0 and 1. So that's why it's the fractional order differential, fractional order equation. And the state xt, this state xt that is lying in capital X, there's the Hilbert space, or we can say this xt is the X value stochastic process. And this control term ut that is lying in a separable reflexive Hilbert space, you can say capital U or script U, something like that. B is a linear operator, A is the infinitesimal generator of an resolvent operator, you can say as alpha t. F is a nonlinear function lying from the interval to the state space X to X. The sigma is nothing but the interval to the X, and that is lying in one space, and that is L2 0 q to the power half yx. I will let you know why I chose this space. And this one is nothing but the Rosenblatt process. This H is nothing but H is from the interval to the capital X, the state X, and the control space, and to X. And tilde dx du, that also we will define after a few minutes. This x0 equal to x0, that is nothing but the psi 0 measurable x value stochastic process independent of this Rosenblatt process with the finite second moment. Why I said finite second moment, that also we will let you know. We will come to know very soon. Let me continue with these system components because we are working with the stochastic process, and that's why we have to have some probability space. So let omega, psi, and p be a complete probability space furnished with the complete family of the right continuous subsigma algebra psi t. And this psi t that is in psi, that belongs to psi. And this is actually nothing but the sigma sub algebra, and that is generated by this Rosenblatt process and the p null set. And ZHT, that is the Rosenblatt process with the Hust parameter H lying between half and 1. And the collection of all strong measurable square integrable function that is given by L2, omega, psi, and x. Shortly, that is given like this. And this is with respect to the norm of x in L2 that is equal to expected value of xt square and half. And it is easy to prove that this one is a Banach space because one can take the Cauchy sequence from this and try to prove the completeness of the Cauchy or convergence of the Cauchy sequence in the same space. So the space will be complete, and that's why one can say it's a Banach space. Let me continue with again the system component. Suppose Lyx denotes the space of all bounded linear operators from y to x. And if I take y equal to x, in that case, I would like to denote this one by just L and y. And this q belongs to any operator q lying in this space y. That is a non-negative self-adjoint operator. And I want to define the subspace y0 that is equal to q to the power y of y, which endowed with the inner product uv at y0, and that is equal to q to the power half u and q to the power half v, and Y. So that's how this subspace and this space is related with the Hilbert space. And L20, that is nothing but the space of all Hilbert's Kimmich operator. When you define the space on Y0 to X, that is the space of all Hilbert's Kimmich operator from Y0 to X. And phi is another operator in L20 now, that is called this Hilbert's Kimmich operator, satisfying this norm of phi squared, that is equal to summation of this one, and that is finite. And that is with the inner product like this. And if you take phi equal to psi, in that case, we have norm of psi square that is equal to this one, and that is nothing but the tracing. We require this space of continuous function from the interval to the L2 space, and that is a Banach space of all continuous function from this interval to the Banach space, as I told you, satisfying the sup norm of the expected value of xt square is finite, and x2 be the subspace of this one, this space, continuous space. And there is measurable site adaptive and x valued process where x belongs to this one equipped with this norm. So that's all about almost all about the system component. The last portion that is left out, that is n tilde ds du. That's what we have defined in our system. So suppose that qt is the Poisson point process taking its value in the measurable space ubu with the sigma finite density intensity measure, and this n tilde ds du, that is nothing but the compensating martingale measure and the Poisson counting measure, and that is given by this one. So that's all about the system component. And now, we have defined the psi-t, that is nothing but filtration, but actually that filtration that is defined in this form. And this filtration, psi-t, and that is produced by qt Poisson point process, and that is augmented matrix. So where n is the class of all p-null set, this n is nothing but the class of all p-null set, and p2 from this interval to control space x to x be the space of all predictable mappings h1 satisfying this condition. You know that we are going to learn about the controllability, it's optimal controllability. That means we have to have some cost functional. So that cost functional that is given in this form related to the context of the problem. The admissible set UAD, the set of all collection of all the operators VT from this interval cross omega to U, such that we cite adaptive stochastic process with the expected value of the integral of norm of V that is finite, Pth norm is finite. And this UAD that is contained in LP space, that is bounded, convex, and closed operator. And we denote by this set of all admissible control pairs, X and U. This X and U that is equal because this X stands for the state variable, state variable, and U is nothing but the control. And that's why we have this order pair in terms of X and U, and that is in AUD. So this XU, that is this X is nothing but actually the mild solution of our system corresponding to our control U in UAD, because U is lying in UAD. So the main objective is to find the another order pair X0, U0 in UAD such that this XU, order pair XU, that is convergent over here to XU, U0. And once we are able to find this one, that means we can say that our system is optimal controllability can be obtained. So main objective of this work, that is, as far our knowledge, no work has been reported based on the optimal controllability of the fractional stochastic integral differential system driven by the Rosenblatt process and the Poisson sum. As I told you that I had lots of discussion with the reviewers, 2-3 reviewers based on this second part, that is, we know that fractional Brownian motion can be approximated by the Wiener-Ito integral of type 1. So what's about the Rosenblatt process? Because there are some consequences. So finally, I just try to explain to the reviewers that how can we approximate the Rosenblatt process also. The Rosenblatt process can also be approximated by the Wiener-Ito integral of type 2. So that's what we are going to discuss over here. And then after the rest of the work, that is very simple, because we are going to learn about the existence and uniqueness of the optimal controllability with some examples. So let me start with this preliminary. And as I told you that I would like to start with the Wiener-Ito stochastic integrals. So let BT, T belongs to R. Of course, this BT is not same as the B we have considered in our system. So you can consider that is equal to B1T if you want, just to separate it out. So B1T, T belongs to R with the standard Brownian motion with B0 equal to 0 and the Wiener-Ito integral of order M that is given in this form. IMF that is equal to integration RM, and this is just a prime f of x1 to xm, dx1 to db, dbx1 to dbxm. This f is nothing but this f is the non-random kernel, and dbx can be interpreted as the Gaussian noise mean 0, and the variance dx. With expected value of dbx1 and dbx2 equal to 0 if x1 is not equal to x2, and that is dbx square is equal to dx. Here the prime indicates that one cannot get the integration over the diagonals. So that is not possible. And that is, one always supposes that x1 is not equal to x2 is not equal to xm. And this ensures that this expected value of dbx1, dbx2, dbxm is equal to 0. And that's why I would say that IMF, this operator, this has the mean 0. And we have this estimation that IMF that is equal to, this is a distribution, and this distribution could be anything. It could be a martingale distribution or the joint distribution depending on the context of the problem. And this F symmetric that denotes the symmetrized version of my operator F. And integral 3, whatever I presented over here, this integral 3 can also be viewed in the form of, that means that satisfies the norm of in L2 such that integration of Rm of f of x1 to xm square dx1 dxm, and that is finite. And that is for all f in L2 Rm. If you want to define this integral, we can start with a simple function, and then after we can take the limit in L2 Rm. And by ensuring that the isometry of this one that is given like this one. So m factorial norm of f square L2 norm, of course. And this, if you take m equal to 2, that means it denotes the cumulants. So if f is symmetric, then thanks to Fox and Teku, they have proved this result. When f is symmetric at that time, we have this estimation. And it is also possible that whatever the equation 3 we have seen over here, this equation 3 can also be represented slightly different way. And that was also given in the book of the paper of Fox and Teku, that you can represent that one in the form of IMF equal to, again, the distribution of Rm, and this is double prime, f tilde lambda 1 and to lambda m, and db tilde lambda 1 to db tilde lambda m, where this f tilde lambda 1 to lambda m, there is nothing that is given in this form 1 over 2 pi to the power m by 2. Again, the same thing that is proved over here in this paper. But what is this? This is nothing but the Fourier transform of f in L2 and this f in L2, and this db tilde that is viewed as a complex Fourier transform of dbx. And because of dbx is real, so db tilde can satisfy db tilde equal to db tilde negative lambda. And thus the integral given over here, this integral that is the double prime over here, that means that again one cannot take the integration for lambda 1 equal to plus or minus lambda 2 equal to plus or minus lambda m like this. So this is made precise. Again, the same thing, why we cannot take the integral that was given in the book of, or I would say paper of Teku, where the equality in the distribution between 3 and 6 that is established. And we have this relationship, that estimate value of IMF square that is equal to this one. Now you can see over here in all the axes over here that is given in terms of time, and all the lambdas are given in terms of frequency. So we have time and frequency domain, and that's why we have the Fourier complex transform, but one can extend the same result for the wavelet transform too. Dobechi, the professor over here in Princeton University in New Jersey, I got the opportunity to meet her twice. Once when I was in Korea for ICM conference, Seoul, South Korea, and once over here in New Jersey. So we held some good discussion. She wrote really very nice book based on the wavelet transform, Introduction to Wavelet Transform. If somebody is interested, he or she can refer that book too. Lots of, because you are working with the time and frequency domain. So I think that's a very nice book. So I just recommend that book if somebody is interested. Anyway, so we are working with time and frequency domain over here. Just keep in mind this thing. And now I just would like to give you the stochastic representation of fractional Brownian motion. So we have just gone through some of the things about the Wiener-Ito process, and now the stochastic representation of fractional Brownian motion. So to better understand this Rosenblatt process, it is always useful to first understand the concept of the fractional Brownian motion. I denote this one by just FBM. And the fractional Brownian motion that is characterized, usually I denote by VHT t greater than or equal to 0, that is characterized by these three conditions. The first one is the Gaussian mean 0, so stationary increment with BH equal to 0, and the self-similarity index H lying in 0 to 1, and that is for any constant A greater than 0, BHAT t greater than or equal to 0, and A to the power H BHT t greater than or equal to 0 have the finite dimensional distribution. So we will keep these three conditions handy because we are going to use the same thing for our Rosenblatt process too. So actually what we mean by the stationary increment and the self-similarity index. So stationary increment is that is given by this one, the self-similarity index, that is this one, and stationary increment that is given by this one. Equation number 7 and 8, again, that was proved, that is in the book, or it's a paper of Fox and Taku. Okay, and if you take over here sigma square equal to 1, in that case, we have this sequence, because that is nothing but the increment of this fractional Brownian motion sequence of this one. So BHK plus 1 minus BHK, that is given by this one. So this sequence is Gaussian, stationary, and the long range dependence for H lying between half and 1 with this rank condition. And this condition is satisfied, and you can take that 2 minus 2H, that is some D, some representation, some symbol D. And YK is called the fractional Gaussian noise. You must be wondering that why this fractional Gaussian noise factor is useful over here. Let me just give you one of the applications over here. Suppose you want to hit the warplane with the help of the missiles. Missile is on the ground, warplane that's in the air. You have two different spaces. So you want to hit the warplane with the help of the missiles, and that's why you need to give some proper control to the missile so that it can hit the warplane in the proper time period and the proper decided place. When the warplane is there in the air at that time, lots of noise is there in the surrounding region. Whenever we are working with the exact controllability or the complete controllability, that means mostly we are ignoring this factor, but practically you cannot ignore that part because noise factor is affecting on so many other factors too. So practically you cannot ignore. I would prefer you guys to read the paper of Balakrishnan. He was an electrical engineer, and I think he published that paper almost in around 84, 85 in IEEE. And he proved this result that one cannot ignore the noise factor. Of course, that paper that was in the finite dimension, and then after people have extended that work in the infinite dimension too. So that is the main use of the noise factor. So when we take the same thing in terms of the practical aspect, practical problem. Anyway, so now I would just like to go through the stochastic representation of the Rosenblatt process. So whatever the stationary increment and a self-similarity index we have seen for the fractional Brownian motion, fractional Brownian motion, the same thing. Fractional Brownian motion I denoted by BH, Rosenblatt process I denoted by ZHT or ZT. So let me just give like this expected value of Z square T that is given like this one, and the same thing. So same self-similarity index that is satisfied by the Rosenblatt process too. That was also proved in the book of Tudor. We have several representation of the stochastic, the Rosenblatt process. That is a time representation, fractal representation, finite time interval representation of the Rosenblatt process, etc. The properties, as I told you, that Tudor and his student, they have proved some properties just before a few years, and that was based on Rosenblatt process. That's what I would like to discuss over here. So the Rosenblatt process ZT greater than or equal to 0 has as an almost sure continuous path version, and that is given by expected value of ZT1 minus ZT2 square equal to T1 minus T2 to the power 2H. And this 2H is greater than 1. And thus it satisfies the Kolmogorov criteria. And that was proved over here in this reference. But the main thing is the Rosenblatt process is not differentiable. See, the fractional Brownian motion is differentiable, but the Rosenblatt process is not differentiable in the mean square. And that's why people think that Rosenblatt process cannot be approximated by the Wiener-Ito process or Wiener-Ito integral. But that's actually the wrong thing. Why people are thinking like this? Let me first explain to you this thing. The Rosenblatt process is not differentiable in the mean square because in the same book, it has been proved that limit t tends to 0, expected value of zt over t squared, that is equal to limit t tends to 0, t to the power 2h minus 2, and that is infinite. And this is almost surely non-differentiable because of this one. And the argument is based on the self-similarity and is identical to the one of the fractional Brownian motion too. Again, as I told you, Tudor. So we have seen the Rosenblatt process is self-similar with index lying between half and 1 as a stationary increment, and therefore we can have the increment like this, just like the fractional Brownian motion. So zk plus 1 minus zk, that is, let me denote by delta zk, and long range dependence that is given in this form. So in fact, we have the exact same covariance as the increments of fractional Brownian motion. I can write the same thing in this one, for this same form too. Delta Z0 and delta Ck, expected value that is given using the self-similarity index. And Yeah, so self-similarity index and the covariance. So we've represented some of the several representation of Rosenblatt process are there. Out of these several, we have just represented 2 or 3. While representation is not that physical, we do not provide immediate information about the distribution. And since the Rosenblatt process is represented as a double winner integral, winner-Ito stochastic integral. Please keep in mind this thing. That's what our aim. That's what I just would like to let you know. One can use the general result due to Mazur. Mazur, he proved this thing, that there exists some constant C greater than 0 such that probability of Z1 greater than U, and that is less than or equal to some constant C, and this one, where sigma square, that is nothing but the expected value of Z1 square. And this result that was proved, actually the hint was given over here in the Mazur, but the result was actually proved by Ren and San. And then after, thanks to Albin, the result one actually that was proved like this: probability of the supremum of CT that is greater than U is greater than or equal to probability of Z1. But Albin says that if you take the limit supremum of probability of supremum of ZT greater than U and U to the power 1 minus H over H, probability of Z1 greater than U, that is finite. This indicates, this gives us really fantastic result, because U to the power 1 minus H over H, this tends to infinity as U, and 1 minus H divided by H, that decreases from 1 to 0 as your H reduced parameter increases from half to 1. And that's why we have the very nice result. That means we have this probability, similarity index between this probability of supremum of ZT greater than U and the probability of Z1 greater than U. So that result that was proved by this Albin, thanks to him. And because of that result, now we have the martingale distribution of ZT as a probability density function. And this follows from the general result of the multiple integral too. So as remarked previously, the Rosenblatt process can be viewed heuristically as the integral of its derivative. See, Rosenblatt process is not differentiable, but it can be viewed in the form of the integral of its derivative. We are in the LP space. And however, Tudor says that one can use the point at this point of view to show the Rosenblatt process can be approximated by the sequence of semi-integrals. Now, Rosenblatt process can be approximated by a sequence of semi-integrals that was proved by Tudor. Once we have this one, that means we have to have the sequential form of the Rosenblatt process, and that sequential form that is given in this form, that Z sigma T that is given by this distribution and blah, 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 this is the thing. And this prime that is in this form. And since the expected value that tends to 0 as sigma tends to 0, one obtains the Rosenblatt process can be approximated by a sequence of semi-martingales. And this sequence of semi-martingales that can also be viewed in the form of the bounded variation. The extension that was something like this, the Rosenblatt process can be approximated by a sequence of semi-martingales. Sequence of semi-martingales can be viewed as the extension, I would say, in the form of the bounded variation. And this bounded variation can be extended in the form of the Rosenblatt process can be approximated by the integrals, winner-Ito integrals of type 2, means the double integration in LP space, of course. So that's what we are going to see. So winner-Ito multiple integral of order K that is given in this form to the standard Brownian motion that is in this form, where this X plus that is given by maximum of this one, some components are there. And the Rosenblatt process with the parameter, reduced parameter that is given in the form of ZH has the following integral. Please look at over here. This integral looks very complicated because this W that is given in this form, this operator WT, T belongs to this one, is a winner process. H dash that is given by H plus 1 by 2. Constant, the CH that is given in this form is a normalizing constant, K to the power H, TS, that is the kernel given by this form. Yeah, so that's why I told you, very complicated equation that was proved by Tudor. And this KH that is actually given in this form, but this here in this integral also, this CH is given in this form, where this beta that represents the beta function. So that's how this integral they have proved. And if we prove that, or if you put this KH TS equal to 0 for T less than or equal to X, then we can say that for every S and T greater than or equal to 0, the covariance of the Rosenblatt process that is given, that's satisfying this condition. So covariance is satisfying this condition. Q is the operator in Ly to Y, I mean to say Ly space, the operator defined by QEN, and with the finite trace, this one. And psi t, as I told you, that's just the filtration. So please keep in mind this thing. Z and T, that is the sequence of two-sided one-dimensional Rosenblatt process mutually dependent in our probability space. And consider the y-valued stochastic process ZQT given by this one. If Q is non-negative self-adjoint trace class operator, then this above series that is convergent in the space Y. And thus the Rosenblatt process is approximated by the Wiener process. So that's how the work has that was developed, that Rosenblatt process that was approximated by the Wiener, I mean to say, sequence of semi-martingales to bounded variation to the Wiener-Ito process with integration m equal to 2. And then after people have used the same result and try, just in last 1.5 years, people have tried to prove some of the results based on Rosenblatt process, not the optimal controllability, but with the Rosenblatt process in last couple of years. Now, let me just go through again, thanks to Tudor, because Tudor says he proved this result. Now, you know that whenever we are working with the exact controllability or the, I'm to say, complete controllability at that time, what we do at that time, we are usually using the dominated convergence theorem for the real space. But here we are working in the stochastic space and probability space, and that theorem that's not true for the stochastic space. And that's why, thanks to Tudor, he proved this result, and he said that whenever your operator is lying between 0 to tau 12 to 0, satisfying this norm, integration of this norm is finite, then you have expected value of the norm of the integral is less than or equal to constant and integral of its norm. Just looks like the dominated convergence theorem, but not exactly. This is just for the stochastic process. And then after we have the Riemann-Liouville fractional integral operator that is in the form of this f, that is I alpha, again alpha as you know that lies between 0 and 1, f of t that is given in the form of 1 over gamma alpha, gamma function, and integration 0 to t, t minus s alpha minus 1 fs ds. Usually people think that, including me, that we cannot work with the Riemann-Liouville function because the constant derivative of the constant to Riemann-Liouville that is not 0, but derivative of constant is 0 due to the Caputo derivative. And that's why I would just like to go for the Caputo derivative. But as Ristova from Bulgaria, I got the opportunity to meet that lady last year when I was in Europe. At that time, we discussed 20-25 minutes out of the conference place, because after the conference, we had some free time. And she said that people are working with Caputo fractional derivative, but actually that is wrong. She said that she did some research with Professor Agrawal here in Florida University of Florida, I'm sorry. And for a couple of years, and she came to this conclusion. And I had some arguments, so I discussed with her, but finally she said, no, we can work with only Riemann-Liouville function. Some recent developments are there. She published a couple of papers. So I think one can go through it. Somebody is interested, but I don't want to make any comment whether that is true or false. I think one can read the paper because it will take some time for me to convince this thing, because anyway, so that's just another development in the same field. Anyway, so two parameter fractional function of the Mittag-Leffler type that is defined in the series expansion, this form where this C is nothing but the contour, and this lambda, norm of lambda that is bounded by this one, the clockwise. The resolvent operator, now we are not working just only as I told you that A is the infinitesimal generator of what we say, the resolvent operator, but we are working just on one sector of that resolvent operator, and that's why I want to give you the definition of the sectorial operator. The sectorial operator that is given in this form with this condition, the resolvent set of A that is contained in this one, and this resolvent that's norm of this one that is bounded by this one. The extension of the same one, the sectorial operator that is given over here, and both the things they are given by Su and Chan. So now we are in a position to at least confirm a little bit about the Cauchy problem. So if we have the Cauchy problem, then the mild solution, I'm not talking about talking about our problem, system one. I'm just talking about right now one simple Cauchy problem, because we are going to take the help of this Cauchy problem to define the mild solution of our problem. So my Cauchy problem, there is something in this form, fractional order simple system, and mild solution that is given in this form with some semi-group that is given by S alpha t and the resolvent operator that is given in this form. And naturally, this semi-group and resolvent operator, they are bounded by this one, ms and mt. You can see over here. So because of the limitation of time, I think, yeah, let me just almost I took 28, 29 minutes. So I don't have enough time to go through all the details. So let me just go for this one, because these are just the mechanical process. So I think one can go through this one very easily. Anyway, so now we are in position to define the mild solution of our system 1. So and psi t adaptive filtration, adaptive stochastic process xt in the space of continuous function that is called the mild solution of system 1 for each control u in LP, and this is script q, is measurable and the following stochastic equation is satisfied. You can see over here xt equal to s alpha t. As I told you, resolvent operator, I mean semi-group and the resolvent operators are there. BUT, F of this one, and T alpha, sigma, Rosenblatt process, H, and N tilde. So mild solution that is given in this form. Now the main part is almost over, and now I would like to give you the existence and uniqueness of our system 1. So for existence and uniqueness, I require a few more assumptions. So like my function, nonlinear function F is Lipschitz continuous, sigma is Lipschitz continuous. No, function H satisfies little weaker notion, L1 Lipschitz continuous, and operator B lying over here in this space, and norm of B stands for the norm of the operator B in the Banach space L infinity. And the map, this sigma, that is the multi-valued map, and that is convex bounded value, and the graph measurable function. So we require this of the some of the hypotheses, or I would say assumptions like this. Using this one now, what I would like to do that is using these assumptions H1 to H3, that we say that we have unique mild solution on our interval for each control U in UAD, and for each P such that P alpha greater than 1. So we want to prove that, first of all, I just would like to assign an operator with my mild solution. So my mild solution with the operator G from x2 to x2 that is given in this form. And our aim is now to, because our mild solution already defined, so our aim right now is to prove that this operator G has a fixed point. And that's why, first of all, I just would like to know this thing, that Gx2 that is contained in the space x2. Gx2 is contained in the space x2. And that's why I just would like to take one operator x from x2, and we are going to prove the boundedness. So I would like to assign some different operators. Suppose this is gamma 1, and here to here there is gamma 2. And it has nothing to do with some gamma function, it's just the representation. Please keep in mind this thing. And here to here there is my gamma 3. This is my gamma 4 and gamma 5. It's very obvious to prove because we have those H1 to H3 assumptions. So we can use these assumptions and try to prove the boundedness. That boundedness I have proved over here, gamma 1, gamma 2, gamma 3. Gamma 1 is obvious. Squares inequality, Cauchy squares inequality I have used over here to prove gamma 2. And then after we can go for gamma 3. Again, the Cauchy squares inequality from here to here. That is my gamma 3. So that is also bounded. And then after I have used the assumption H1 to prove the boundedness of gamma 4, and finally gamma 5 too. So finally I have the growth condition for the expected value of my operator Gxt square, that is like this. So A and B are the suitable positive constants. So G maps from X2 into itself. So now the only thing is left out, that is G is a contraction, because if I prove this thing, then after using the Banach contraction principle, I can say that existence and uniqueness of the solution of the system that is valid. So contraction, that is quite easy. You know that contraction fx minus fy is less than or equal to constant less than 1 and norm of x minus y. The same thing over here for the stochastic process too. So expected value of gxt, sorry, gxt.
Excuse me, sir.
Yes.
5 minutes more.
5 minutes more?
5 minutes more.
Okay, thank you. Thank you. I will try to finish this one in 5 minutes. So expected value, that is one, this is the contraction. So contraction can be proved like this, and because this was the assumption, and that's why G has a unique fixed point, which is a solution of the system. And then after one can prove other way the boundedness of this one. So that boundedness can be obtained using the Holder's inequality. So let me skip that part, and now let's go for the optimal control. For optimal control, I require one more assumptions, that my operator L, that is from this space, and that is continuous, I would say, measurable with respect to the first variable, and lower semi-continuous, sequential lower semi-continuous in terms of second and third variable. And for D greater than some constants D and E, we have this estimation. So using this one, I just would like to prove the optimal controllability, that JXU. So we are looking for this type of optimal pair so that we have the sequence XN, UN convergent to X0, U0. And here you can see that because my LT, my sequence is like this, suppose that is finite, then in that case, what I'm going to take that L of XM and UM that converges to sigma as M tends to infinity. I would like to take both the terms separately. UM, so I would like UM that is contained in UAD for M equal to 1, 2, 3. And UM is bounded subset of the separable reflexive Banach space. And there exists a subsequence. Because it is a bounded subspace of separable reflexive Banach space, I would like to prove that a subsequence is convergent weakly, and that's why my sequence is convergent strongly. So that concept I have used over here to prove that this sequence UM that is convergent to some U0 in UAD. And because my UAD is closed and convex, so by Mazur lemma, we can say that this U0 also lying between UAD, and that's why I can say that UM is convergent to U0. For my state space on mild solution, I would like to take the sequence XM equal to in this form mild solution, and I'm looking for X0 also. So whenever I have XM and UM, X and U, I just would like to consider the sequential form XM and UN. And same over here for X0 also. And then after, because I want to prove that XM converges to U0, I just would like to take the norm and try to use the Cauchy-Schwarz inequality. And I have proved that XM minus X0 that is less than or equal to this one. But my operator B is strongly continuous, and that's why this B or BUM converges to BU0 strongly. So naturally my XMT converges to X0T. And thanks to Baldwin, because Baldwin said that once you have the convergent sequence of your mild solution and the convergent sequence of your control, then you can take the order pair, and order pair can also be, you can say by Baldwin's theorem that order pair is convergent too. So that's how we have the optimal controllability, because XM, that is convergent to X0, U0. So that is the optimal controllability of the given stochastic process. And finally, the example is given over here. This example is, you can see alpha equal to 2 by 3 over here. And my system that is in this form, ZT that is Rosenblatt process, and domain of A that is in the Sobolev space like this, X2 omega 1 intersection, this one has to be very careful defining this space, and infinitesimal generator for this problem that is given in this form, and the control function that is in this form. And you can see over here that whatever my system components with my example, you can compare with this one. So everything that is now expressed in the form of my system 1, and that's why we have the cost functional that is given in this form. And finally, I can say that optimal control per X0, U0 in L2 space cross L2 space. And that's finally, I have this estimation. So whatever the example I just showed it to you, that was just that matches with our assumptions and our system 1. So that's all about the application point of view. And now finally, the conclusion, how can extend the work, whatever I have done over here. So the existence and optimal control of the proposed problem that is presented by using the Baldwin's theorem, and the optimal control analysis for the fractional stochastic differential inclusion with distribution delays one can use over here. I have not used the distribution delay over here, but one can extend the same problem through the distribution delays too. One can use the time varying delay problem. One can use the state dependent infinite delay problem, and impulsive effect too. That would be the future work. The most important thing is one can go through the numerical estimation for the same problem, and that would be really very fantastic work, because whatever the work you have proved theoretically, you have to match the same work numerically to justify your theoretical work. So I think I don't have any time, and it is exactly 45 minutes. So let me stop over here. These are a few references I have used to prepare this talk. If somebody is interested, he or she can go through this one. And I know we have limitation of time, so we don't have enough time for the discussion. But if somebody is interested, these are the main paper I have used over here, TechQ and Fox and TechQ and Tudor. And I have a YouTube link, and you may find the same talk over there on YouTube. If you have some doubt, we can discuss. I will try my best to get back to you if I get some questions from you. And again, thank you so much, the organizer, for giving me this opportunity. Thanks for the invite, and I would like to conclude over here.
Yes, thank you very much, sir, for sharing your profound knowledge with us. That was really an amazing talk on optimal control for fractional stochastic differential systems driven by a Rosenblatt process with Poisson jumps. That was indeed very much beneficial. Now, are there any questions from the audience? I see
Yes,
a raised
yes,
hand from
I
Sanjeev Gupta.
have one question, Professor Charlie Shajar.
Yes, please.
Can I? Yeah. You said alpha equal to 2 by 3 and establish the result.
Alpha equal to 2 by 3. Just I took it over here in the example, alpha equal to 2 by 3, but one can take alpha equal to 1 by 3, any number lying between 0 and 1.
0 and 1. But can
Yes.
we have comparison when alpha is equal to 1? That is standard.
No, ma'am. If you look at the first slide, if you, I strictly mentioned that alpha is lying between open interval and 1. So 1 is excluded. You
Okay.
can take only the number between 0 and 1, but 0 and 1 are excluded.
Okay, because in dynamical system, we take alpha equal to 1 and
Exactly.
compare the
If you
results.
take
That is what
alpha
I
equal to
wanted
1,
to.
it would be converted to dynamical system. So
Dynamical system.
1 is
Okay.
not allowed.
Okay,
Yeah,
thank you.
then that's why I put open interval 0 and 1. It's not closed, it's open. So 1 is excluded.
Okay, great.
Yeah.
Thank you for good exploration about once again a control theory, because we had, in fact, all the lectures were about control theory in
Right.
one or the other way. First
Yes,
one
ma'am.
was in medical science. Second one, how to have optimization. Third one in dynamical system of digital learning. And fourth one, actually the basics of control theory, which is dependent on all the functional analysis concepts. So thank you all the speakers from Department of Mathematics, Gujarat University and Parul University for having such a huge applications of pure maths and in applied maths. So thank you once again for accepting invitation on behalf of Gujarat.
And thank you so much. I wanted to join you guys. I wanted to attend all the lectures, but I'm sorry.
But you could not because it was a night time for you.
Sorry.
It was not possible.
Thank you.
Okay. I request all the speakers, all the panelists to have one photograph, please. Please switch on your video. And Dimple sir, please stop sharing your screen.
Sure. Yeah.
Yes, Dr. Jitendra, will you please take? Jitendra? Che. Kanan, please. Achha, Kanan.
Yes, ma'am.
No, you are at two places.
Yeah,
Bhargav,
thank you,
madam,
Dr.
please.
Jitendra. Thank you, Dr. Kanan, for your organization. Thank you so much for support.
Bhargav, madam, please. Video on. Yes. Now we want actually pick. We want pick. Yes, Jitendra.
Yes, madam.
And then you can move from one of this.
Yes, madam.
Just a minute. Jitendra, Kanan is moving away.
Just a minute.
Yes, ma'am. I have left now. I'll not be visible for the.
Yes, now it is done. Even same is with Bhargav, madam. No problem. Take it. Take a pic.
Doing, madam. Fine.
Yes,
now?
done. Bhargav, madam, please video on.
Yes, ma'am. Yes, ma'am.
Done?
Done, madam.
Thank you.
Thank you.
Thank you all the speakers.
Yeah.
Thank you, sir.
Madam, you are Bhargav,
Thank
madam?
you.
Pardon?
Bhargav, madam is speaking something, but
Tomorrow's password, ID and password.
yes, ma'am, I will send an email.
Okay, thank you.
You use the same link.
Okay. Link is same, but ID and password is also same.
I will send email to all of you.
Okay, thank you. Thank you.
Yeah,
This is
please share with us.
And Jitendra, be ready, huh? Because
Yes,
we
madam.
all are having some or the other issue.
No problem, madam. I am ready. already.
Even after doing so many webinars on Zoom, I found problem. So be there.
Okay, madam. I will be there.
Bye, everybody. Dimple sir, good morning.
Good morning. Thank you.
Good morning, sir.
I'm leaving because I have another meeting.
Yes, sure. Thank you
you.
so much. Yeah.
Thank you, ma'am.
Thank you.
Okay,
ma'am.
thank you, sir, everybody. Just fine.
Thank you
sir.
so much, everyone. And
Thank you, all of you.
tomorrow's session we will be having at 2 p.m. IST. So I believe that we'll be joining at 1:45 p.m. IST. Thank you so much for your presence today. I hope on behalf of Gujarat University and Parul University that you all might have enjoyed today. And our conference is yet to have the second day, that is tomorrow, 27th of September 2020. See you tomorrow, sharp at 1:45 p.m. IST. Thank you so much, everyone. Thank you.
Okay, see you.
Thank you. Bye.
Bye. Thank you. लाइव स्ट्रीमिंग बंद क्या थी थसे
रिमूव कर रहा हूँ, वो एक ही जना अंदर है। હોસ્ટ હોય આપણે જે વાત થઈ હતી ને, હોસ્ટ કો હોસ્ટ પછી બધા હોસ્ટ થઈ જાય।